7,600 light-years from the room you are in sits Eta Carinae, a star so far we can barely fix its position, and yet in the 1840s it crossed all that distance to become the second brightest point in the night sky. Then it did something a star burning that hard should not survive. It threw off more than 10 suns of its own mass in a few years, and it is still there tonight, unstable and somehow holding together. And if somewhere tonight this star gives you something to carry into sleep, a little wonder, a little quiet, then a like or a subscribe would mean a great deal to me. Not for any algorithm, just so I know you were here in the dark with it. Two centuries of watching, and we still cannot agree how far away Eta Carinae really is, or how close its coming death would throw its radiation toward us. And the harder we look, the less sure we are that it is one star at all, or the wreckage of 3 that collided long ago. The real distance is only where the trouble starts. 7,600 light-years, 4 small words, and the mind slides right past them. But a light-year is not an amount of time, it is a length. The distance light travels in 1 year, and light is the fastest thing this universe permits anything to be. So the honest way to hear that number is a little slower. Light itself, moving at the one speed nothing in existence can outrun, needs 7,600 years to carry the image of Eta Carinae from where it burns to where you are lying right now. To feel how far that actually reaches, start somewhere closer, with the nearest star to our own sun. Alpha Centauri sits a little over 4 light-years away, and even that step is one no machine we have ever built could finish in a single human life, or in 500 of them stacked back to back. Now take that already impossible gap and lay it down again, end to end, nearly 1,800 times. That is roughly how much farther Eta Carinae is than our closest stellar neighbor. The fastest craft we have ever flung out of the solar system, moving somewhere near 60,000 kilometers an hour, would need on the order of 130 million years to cross that distance. The last dinosaurs were still walking the Earth that long ago. There is something stranger sitting inside that number, though. With a gap that enormous, you might expect this star to live out at the ragged rim of the galaxy, off in the thinning dark where the Milky Way frays into empty space. It is nowhere near the rim. Our galaxy runs about 100,000 light-years from one edge to the other, a slow, flat wheel holding a few 100 billion stars, and our sun rides well inside that wheel, roughly 26,000 light-years out from the packed and blazing center. Set 7,600 light-years against a wheel that wide, and it stops looking like a voyage to the edge of everything. It becomes a short reach across our own corner of the galaxy. Picture the whole galaxy as one enormous building, and every star a room inside it. Our sun is one lit room among hundreds of billions, somewhere in the middle floors, and Eta Carinae is another lit room a little way down the same long hallway. Not in another building, not across some cosmic gulf between galaxies. Just farther down the corridor we already live in, close enough that on the scale of the whole structure, the two of us are almost neighbors. That is why astronomers talk about this monstrous, violent, faraway star as if it were nearby, because by the measure of a galaxy 100,000 light-years across, it truly is. And yet nearby, here, does not mean reachable. These two facts refuse to share a sentence comfortably. Eta Carinae is a neighbor. Eta Carinae is a place no human hand will ever touch, no probe will ever photograph up close, no message will ever reach inside a civilization's lifetime. Send a signal toward it tonight at the speed of light, the fastest a signal can go, and it arrives in 7,600 years. Any answer takes another 7,600 to come home. A single exchange, one question and one reply, would outlast every language now spoken on this planet. So we do not go to Eta Carinae, and we never speak to it. Everything we know about it, we have learned by sitting still and reading what its light carries as it arrives. That is the quiet trade the whole subject is built on. We cannot cross the distance, so we let the distance come to us, one stream of ancient light at a time, and we try to reconstruct a star from what that light is willing to tell us. It is closer to reading a person entirely through the letters they mailed than to meeting them face to face. The letters are all we get. The letters are enough to fill years of study. We have watched this particular star with real instruments for about 200 years. We have measured the color of its light, mapped the shape of the gas around it, timed its rhythms down to the season. By any reasonable standard, we know Eta Carinae well. We can describe how it behaves, how heavy it is, how it throws its own material into space. But ask the plainest question of all, the one the whole night is named after, and the certainty quietly falls apart. Exactly how far away is it? After 2 centuries of careful looking at a star we call a neighbor, why can no 2 methods of measuring quite agree on the answer? Hold a finger up in front of you, look at it with one eye, then the other, and it jumps sideways against the far wall. Nothing about the finger moved. What moved was your vantage point, from one eye to the other, and that small change in where you look from is enough to make a near thing slide against a distant background. We measure the distance to stars the same way, except our 2 eyes are the 2 ends of the Earth's orbit. We fix on a star in winter, then look again in summer from the far side of the sun, and we watch how far it seems to shift against the fainter stars behind it. The larger that shift, the closer the star must be. This one piece of pure geometry, called parallax, is the only distance ruler we have that leans on no assumptions at all. And for Eta Carinae, it very nearly breaks in our hands. The trouble is that the shift shrinks as the distance grows, and it shrinks brutally fast. For the nearest stars, the summer to winter wobble is already a hair's width held at arm's length. Push all the way out to Eta Carinae, and the angle we are trying to catch is smaller than a coin laid flat on the opposite side of the Earth and viewed from where you are lying tonight. To measure a star's distance by parallax, we have to pin its position against the sky that precisely, twice, half a year apart. And that is where this particular star stops cooperating, because to measure where something is, it helps enormously if it holds still and stays the same brightness while you look. Eta Carinae does neither. You might think our newest instruments would settle it anyway. We now have a spacecraft that has measured tiny parallaxes for well over 1 billion stars, angles far smaller than anything ground telescopes could reach, and when we point that catalog at Eta Carinae, it does hand us a number close to 7,600 light-years. But that machine was built for clean, steady points of light, and Eta Carinae is neither clean nor steady. It is blindingly bright, bright enough to overwhelm a detector tuned for ordinary stars. It flickers and surges in brightness on its own schedule. And it does not sit alone against empty sky. It is buried in a glowing tangle of its own ejected gas, inside a crowded knot of massive sibling stars, all of it smeared together. Ask a tool that assumes a still, solitary pinpoint to measure a restless, rapt, oversaturated beacon, and the answer it gives you carries a wobble of its own. We reach for indirect ones, and every indirect ruler comes with a soft spot we have to watch. The oldest approach is to lean on brightness. If we know how much light a star truly pours out, we can compare that to how faint it looks from here, and the gap between the two gives us the distance, the same way a candle of known strength tells you how far off it sits by how dim it appears. But that method quietly assumes we are catching all the light the star sent us, and between Eta Carinae and our telescopes lies a thick, dirty veil of interstellar dust. That dust drinks up starlight and reddens what survives, and here is the part that bites us. The dust in this region does not dim light in the ordinary, well-behaved way most of the galaxy's dust does. Its reddening runs abnormal. Guess how much light the dust ate, and you anchor the distance. Guess it even slightly wrong, and the distance slides by thousands of light years. That single uncertainty is why some careful studies land near 7,300 light years, while others, correcting the dust differently, push the number past 9,000. There is a way out of this, because it lets the star measure its own distance without us ever needing to know how bright it really is. Remember that the eruption blew 2 great lobes of gas outward, and those lobes are still flying apart right now. We can measure their motion 2 separate ways. By comparing sharp images taken years apart, we watch how fast the edges of the cloud drift outward across our line of sight, though that only reaches us as an angle, a little more sky covered each year. And by reading how the gas stretches and compresses the wavelengths of its own light, we clock how fast the near cap is rushing toward us and the far cap away from us, and that motion comes to us as a true speed in real kilometers per second. Now comes the quiet leverage. If those lobes are roughly symmetric, expanding evenly in every direction, then the true sideways speed has to match the toward and away speed we already measured. We know that real speed. We see the sideways motion only as an angle. There is exactly one distance that makes the angle and the real speed agree. And so the nebula, simply by growing, tells us how far away it stands. No candle, no guess about dust, just geometry and time. And that method points back to a distance near 7,500 light years, which is why we trust that neighborhood of numbers even as the others scatter. Still, notice the crack running through even that clever answer. It rests on the lobes being symmetric, expanding smoothly and evenly, and later in this account, that assumption is going to look less safe than it sounds right now. So we are left where honest measurement often leaves us. We can say the distance sits close to 7,600 light years, and we can say it with a margin of a few hundred light years on either side. For something this far, pinning it that well is a real achievement, and we should let ourselves feel the weight of it. But a few hundred light years of slack is not nothing to shrug off. That leftover uncertainty is wider than the entire span of sky separating us from most of the bright stars you can name, wider than the gulf that swallowed the fastest machines we have ever launched. We have measured this star for 2 centuries, and the edges of that one plain number still refuse to close. Every ruler we have used so far shares one hidden thing in common, though. Each of them reads the light arriving from Eta Carinae now, tonight, the ordinary stream pouring straight toward us. But this star sent us another kind of light entirely, light from the eruption itself, and that light did not travel to us in a straight line. It went the long way around, bouncing off distant walls of dust before turning toward Earth. And because of that detour, it is reaching us late, a full human lifetime or more behind schedule. Which raises a strange possibility we have not touched yet. If we can still catch light from an explosion that ended generations ago, what could that late, wandering light tell us that the light arriving on time never could? The answer starts with a simple fact about light that we rarely stop to use. When Eta Carinae erupted, it did not send its light toward Earth alone. It flung that burst outward in every direction at once, a full sphere of light racing away from the star into the surrounding dark. Most of that light had nothing to do with us. It went sideways, upward, off into corners of the galaxy where no one was looking. But the space around Eta Carinae is not empty. It is threaded with enormous sheets and clumps of dust, and when a wave of that eruption light struck one of those distant sheets, some of it bounced. It scattered off the dust and turned, and a small part of it turned toward us. So tonight, we are catching light from the 1840s that never came straight here. It went out to the side first, hit a far wall of dust, and only then started its long fall toward Earth. That detour is the whole reason this light is so late. Think about what a bounce costs you in distance. Light that came straight to us traveled one clean line from the star to here. Light that went sideways struck a dust cloud far off to one edge, and then angled back toward Earth has to cover two long legs of a triangle instead of one short base. The longer road takes longer to walk, even at the speed of light, and so the reflected light lags behind the direct light by more than a human lifetime. This is the same thing that happens when you see a far-off flash of lightning reflected in a distant window, a heartbeat after the direct flash, except here the extra path is measured in light years and the delay stretches from the 1840s into our own century. The star did its work generations ago. The report from a sideways angle is only arriving now. We did not go looking for this on purpose. In the early 2000s, astronomers comparing images of the sky around Eta Carinae noticed faint patches of light that seemed to move and brighten from one year to the next, creeping across the dust like a slow searchlight. Those moving patches were the eruption's light sweeping outward across the dust sheets, lighting each one up in turn as the wavefront reached it. And once we understood what we were seeing, we realized we could do something that should not be possible. We could point a modern telescope at that reflected glow, spread its light into a spectrum, and read the fingerprint of the Great Eruption itself. Not a description written down by someone watching in the 1840s with the naked eye. The actual light of the event, captured with instruments those early observers never had, arriving a century and a half late but still carrying everything it always carried. Sit with where that leaves us, because it is genuinely strange to be inside of. The people who first saw Eta Carinae flare are long gone. Every astronomer who stood under the southern sky in the 1840s and watched that star climb toward the top of the brightness charts lived out their life and died without ever knowing what the eruption was made of. And yet the light they watched is not finished arriving. A portion of it took the scenic route, bounced off a dust bank light years to the side, and is only reaching our telescopes in our own time. We are, in a real and physical sense, watching an event none of us were alive for, reading a broadcast that left the transmitter before our great-great-grandparents were born. The eruption is over. The light of it is still on its way in. So we read that late light, and it did not tell us the tidy story we expected. Here is what we thought we knew. Eta Carinae is a star that drives a powerful wind off its surface, a steady gale of gas streaming outward at a few hundred kilometers a second, and the obvious guess was that the Great Eruption was that same wind turned up to a violent extreme, an enormous but essentially ordinary outflow. When we finally read the eruption's own light, part of that picture held, and part of it cracked. Because tucked inside that spectrum was material moving far faster than any wind has a right to move. Not a few hundred kilometers a second. Some of it was racing outward at something closer to 10,000 kilometers a second, fast enough to cross the distance from the Earth to the Moon in under a minute. That is not the speed of a strong wind, that is closer to the speed of debris thrown off in a genuine stellar explosion. And the surprises did not stop at speed. When we measured the temperature written into that light, the eruption looked cooler than our models had assumed it should be. A blast that violent, in the standard picture, should have glowed hot and blue. Instead, the fingerprint we read back matched something closer to a cool, swollen supergiant, more the color of a dying ember than a searing flame, even while it was hurling out that impossibly fast material. So we were handed a contradiction to hold in both hands. The eruption was, in one breath, too cool to fit the simple wind story, and far too fast to fit it either. A gentle explanation, and a violent one, both true of the same event, at the same time. A star quietly shrugging off a heavy wind does not fling knots of gas at 10,000 kilometers a second. Something more sudden, more explosive, had to be involved. Some event that could deliver a genuine blast of fast debris and yet leave the star standing afterward rather than blowing it to pieces. That is a hard thing to arrange. An ordinary supernova moves debris at those speeds, but an ordinary supernova also destroys the star that made it, and Eta Carinae is still here, still shining, still throwing tantrums on its own schedule. So the late light did not close a case for us. It pried one open. It told us the 1840s event was more violent than a wind and stranger than an explosion, and it left us needing a mechanism we had not yet named. Everything since has circled back to that reflected glow. The direct light of Eta Carinae tells us what the star is doing tonight, its color, its rhythm, its ongoing storm. The echoed light tells us what it did in the eruption, and the two do not fully agree, which is exactly why this star refuses to settle into one clean explanation. We came to that light hoping it would confirm the picture of a supergiant venting an enormous wind. We left it knowing the truth was faster, cooler, and more sudden than that, and knowing we would have to look much harder at the eruption itself to understand what could have happened. So the question the echo forces on us is the one we turn to next. What actually happened in the 1840s, close up, that could throw matter at the speed of an explosion and still let the star live? For most of recorded history, no one looking up would have picked this star out of the crowd. When Edmund Halley catalogued it around 1677, he marked it as a fourth magnitude star, the kind you can see on a dark night but would never think twice about, one modest point among thousands. If you had shown an early astronomer that faint speck and told them it would one day rival the brightest stars in the sky, they would have had no reason to believe you. Nothing about it stood out. It sat in the southern sky for generations, quiet and forgettable, giving away nothing about what it was holding in. Then, over the first decades of the 1800s, we watched it begin to change. The rise was not sudden. It brightened and dimmed and brightened again, climbing unevenly like something struggling with its own weight, until by the late 1830s, it had pushed its way up to first magnitude, into the company of the brightest stars we have. And it did not stop there. In April of 1843, it reached its peak, and at that peak only one star in the entire night sky outshone it, Sirius. Hold on to how strange that ranking is. Sirius is one of our nearest stellar neighbors, a little over 8 light-years away. Eta Carinae, to climb into second place beside it, had to be seen and beaten across roughly 900 times that distance. For a few years in the 1840s, a star nearly 1,000 times farther than Sirius was shining almost as bright to our eyes. To make itself look that bright from that far, the star had to be pouring out a staggering amount of energy. But brightness alone is not the part that should stop us, because a star can flare in light without doing itself lasting harm. The part that matters is what came with the light. This was not a star quietly turning up its glow. It was a furnace throwing out great chunks of its own fuel, hurling material off itself in enormous quantities, and somehow not going out in the process. When we add up everything it flung into space during those years, the total is more than 10 times the entire mass of our Sun. Think about what that means as a quantity. In the span of a few years, this single star shed enough material to build 10 more stars the size of the one that warms our whole planet, and it threw all of it outward into the dark. That ejected material did not vanish. It is still out there, still visible, still moving. It formed the two great lobes of gas we can photograph around the star today, the wreckage of the eruption expanding outward in real time. When we look at that structure now, we are looking at more than 10 suns of a star's own body, torn loose in the 1840s and still flying apart nearly 2 centuries later. And when we measure how much energy the whole event released, in light and in the motion of all that thrown matter, we arrive somewhere uncomfortable. The Great Eruption of Eta Carinae released energy, approaching what a genuine stellar explosion releases. From far enough away, with the instruments we now have, an event like this one would be easy to mistake for a supernova, a star tearing itself apart at the end of its life. We call them supernova imposters. An imposter is a giant eruption that mimics the brightness of a dying star, that flares up on the sky the way a faint supernova would, close enough to fool us at a distance, and then does the one thing a real supernova can never do. It stops. The star survives. The light fades. The crowd of astronomers who rush to call it a stellar death slowly realize the source is still sitting there, dimmed but alive, and the whole thing gets quietly reclassified from an ending into an outburst. Eta Carinae is the closest and best-studied imposter we have, the nearby case we keep returning to, because it let us watch the entire performance without destroying the actor. Now, put the two halves of that together, because they do not fit as easily as they first sound. A true supernova throws off its star's outer layers at tremendous speed, releases energy on this same scale, and in doing so it unbinds the star. The core collapses, the outer body is blown away, and what was a star becomes an expanding cloud with a dense remnant buried in the middle. That is a death by definition. There is no version of it where the star gets up afterward. Eta Carinae released energy in that neighborhood, threw off more than 10 suns of material at high speed, and got up afterward. It is still there. It is still one of the most luminous stars we know of anywhere in our galaxy. So we are left holding a real contradiction. How does a star spend nearly the energy of its own death, shed a tenth of the mass of 10 suns and more, and remain standing to do it all again someday? After its peak in the 1840s, the star dimmed year by year, and by around 1868 it had dropped below what the unaided eye can see, vanishing from the naked eye sky it had briefly ruled. But it did not vanish because it died. Much of that dimming came from the very material it had ejected. The thrown-off gas and dust wrapped around the star like a thick shroud, absorbing its light and hiding the survivor behind the evidence of its own outburst. So the star that seemed to fade toward death was in fact still burning fiercely underneath, simply buried in the debris of what it had done. We were watching a survivor disappear behind its own wreckage and mistaking the smoke for the end of the fire. What lingers with me, when I sit with the timeline of it, is how ordinary the human side of this was. People watched this happen with their own eyes. They stood under the southern sky across those decades and saw a familiar faint star climb, blaze, and slowly withdraw, and most of them went to their graves believing they had witnessed some kind of stellar death, or at best a mystery with no resolution. None of them could have measured the 10 suns of matter in flight, or known the survivor was still there behind the veil. We know those things now not because we are cleverer, but because we arrived later, with better tools, to a story that was still unfolding when we got here. The eruption is history. The consequences of it are still moving fast enough that we can watch them change from one year to the next. And still, for all we have measured, the central question of the eruption remains open. We can tell you how bright it got, how much it threw off, how fast that material moved, how the star hid afterward. What we cannot yet tell you with confidence is what powered it. We do not have a settled, agreed mechanism for how a star delivers that much energy and that much mass in a single convulsion and lives. Every explanation has to clear the same impossible bar. It has to be violent enough to match a near supernova and gentle enough to leave the star intact. To even begin reaching for such a mechanism, we have to back up and ask something more basic about stars this size. What is it that holds a star this massive together in the first place, and how close to falling apart is it even on a calm night? To understand how a star survives spending the energy of its own death, we have to start with the quiet war every star is fighting on, even its calmest night. A star is enormous, and all of that mass pulls inward. Every part of it is falling toward the center, all the time, and if gravity were the only thing at work, the whole structure would collapse in on itself in a matter of hours. It does not collapse, and the reason it does not is that something inside is pushing back out just as hard. For a star like our Sun, that outward push comes mostly from heat. Deep in the core, fusion pours out energy. The gas there is fantastically hot, and hot gas pushes. The inward pull of gravity and the outward shove of that hot gas settle into a standoff, and that standoff is what a stable star actually is, a balance so even that it can hold for billions of years. But heat is not the only thing that pushes. Light pushes too, and that fact is the hinge the whole story of Eta Carinae turns on. We do not usually feel light as a force. Sunlight lands on your skin and you feel warmth, not pressure. Yet light carries momentum, and when it strikes something and is absorbed or bounced away, it delivers a small physical kick, a real shove in the direction it was traveling. You can see this at work without any instruments at all. Look at a comet as it swings near the sun, and its tail always streams away from the sun, no matter which way the comet is moving. The tail points away because sunlight is physically blowing it back, pushing the loose dust and gas outward by the pressure of the light itself. That is not a metaphor for a force. It is the force, light leaning on matter, the same shove that could one day drive a spacecraft on nothing but a mirrored sail spread against the sun. Now carry that idea down into the body of a massive star. Inside a star, light is being generated in staggering quantities, and it has to claw its way out from the core through layer after layer of dense gas. All the way out, that flood of light is pressing on the matter it passes through, scattering off the electrons in the gas and handing each one a tiny push outward. One photon's push is nothing, but the number of them streaming out of a luminous star is beyond counting, and their pushes add up into a genuine outward force, a pressure made purely of light. In the sun, this force is real but minor. Heat does most of the work of holding the sun up, and radiation pressure is a small partner in the balance. As we climb to heavier stars, though, the partnership shifts, and it shifts fast. Because here is the brutal arithmetic of stellar mass. When you make a star more massive, its luminosity does not rise gently in step. It rises far more steeply than the mass does. Double the mass, and the light output can grow by more than tenfold. Eta Carinae sits at the far end of that curve, where the arithmetic becomes almost violent. It carries something like 100 times the mass of our Sun, and for that it pours out light on the order of a few million times what the Sun produces. Try to hold that ratio in your mind. 100 times the material, but millions of times the light. In a classically like this one, radiation pressure is no longer a junior partner in the balance against gravity. It has become the main thing holding the star up. The outward force that keeps Eta Carinae from collapsing is, to a large degree, the pressure of its own light trying to escape. And that changes everything about how stable it can be, because light pressure is a far more temperamental thing to lean on than steady thermal heat. For any given mass, there is a maximum luminosity a star can have and still hold itself together. Push a star's light output up toward that ceiling, and the outward force of the radiation climbs to match the inward pull of gravity almost exactly. Cross the ceiling, and the light is now pushing outward harder than gravity can pull the outer layers back in. At that point, the star can no longer keep its own surface. Its light begins to lift the outermost gas off the top of the star and drive it away into space. That ceiling has a name, the Eddington limit, and it marks the exact edge where a star's radiation becomes strong enough to start tearing at its own body. Below the limit, a star holds. At the limit, it holds by the thinnest possible margin. Above it, it starts shedding itself. The unsettling truth about Eta Carinae is where it sits relative to that edge. It does not live comfortably below the Eddington limit the way the Sun does, with enormous room to spare. It lives pressed right up against it, hovering near the point where its own light can barely be contained. So, when we picture this star on an ordinary quiet night, we should not picture something stable and secure. We should picture a star whose own brilliance is perpetually trying to peel it apart, held together by a margin so slim that it is always on the verge of losing the fight. This is what it means to be one of the most massive stars in the galaxy. Not to be powerful and steady, but to be powerful and precarious. So luminous that your own light is the thing most likely to destroy you. That precariousness is what finally lets us reach back toward the eruption. If a star is already balanced on the knife's edge of the Eddington limit, then it does not take much to tip it over. Some disturbance in the deep interior, some shift in how easily light can push through the gas, and the star can briefly cross the limit and enter a state where the radiation is decisively winning. When that happens, the star does not gently leak. It can drive matter off itself in enormous quantities, launching a heavy outflow powered by the raw pressure of light that has, for a time, overwhelmed gravity's grip. We think the Great Eruption was something like this, an episode where Eta Carinae blew far past its own Eddington limit and for a few years let radiation pressure hurl more than 10 suns of material into the dark. This is still an area where we are reaching, not concluding, and the exact trigger remains debated. But it gives us the first honest answer to our contradiction. The star could spend the energy of a near death and survive, because it was never blowing up its core. It was shedding its skin, driven by a force that pushes outward without ever touching the fusion engine at the center. Stars like this even seem to mark a boundary that nature itself will not let anything cross. When we chart the most luminous stars we have ever found, we notice something strange. Above a certain brightness, the chart simply goes empty. There are no calm, stable stars sitting above that line, only rare, violent, unstable ones like Eta Carinae churning right at the edge of it. It is as if the Eddington limit draws a ceiling across the whole population of stars, and any star that tries to shine brighter than that ceiling cannot hold itself together long enough to sit there quietly. It either sheds mass in convulsions until it drops back down, or it does not last. Eta Carinae is one of the handful of stars living right at that forbidden edge, and its eruptions may be exactly what that struggle looks like from the outside. A star fighting, and barely winning, against the ceiling on how bright anything is allowed to be. There is one more thing that light pressure did, though, that raw balance alone cannot explain. When the star drove all that material away, it did not blow off a smooth, even shell in all directions, the way a simple outward push should. It carved something with a definite shape, two great lobes swelling in opposite directions with a pinched waist between them, a structure far too organized to come from a plain, uniform blast. So the force that nearly destroyed Eta Carinae left behind a sculpture, not a smear. And that shape is a clue we have not yet read. If the eruption was powered by light pushing outward equally, why did the wreckage come out looking like an hourglass instead of a ball? Point a good telescope at Eta Carinae today, and you do not see a star. You see a small, glowing sculpture, two rounded clouds swelling away from a hidden center in opposite directions, with a narrow pinched waist between them where the two meet. The star itself is buried deep inside that waist, so wrapped in its own thrown-off material that for a long time we could barely glimpse it directly. What we see instead is the debris, arranged into a shape so clean and so symmetric that the first astronomers to study it up close could hardly believe a violent explosion had produced something that orderly. Two lobes, one waist, expanding outward together. A blast that came out looking less like a shattered thing and more like something poured into a mold. The shape earned its own name decades before we understood it. In the middle of the last century, an astronomer studying these lobes thought the little double-bodied cloud looked like a tiny human figure, a small rounded head and a broader body, and he called it the homunculus, from the old last word for a little man. The name stuck, and it is a fair one, because the structure really does have that doubled top and bottom form. But naming a thing is not the same as explaining it, and the explaining took far longer. For a plain outward blast, the shape makes no sense at all, and that mismatch is exactly what makes the homunculus worth reading closely. Think about what we would expect if the eruption had simply pushed outward with equal force in every direction. A star is round, and a force that pushes evenly off a round surface should blow a round shell, a smooth, expanding sphere, the way a soap bubble grows evenly in all directions when you breathe into it. That is not what we got. We got two swollen lobes reaching out along one particular axis, and a starved, pinched middle where far less material escaped. Something forced the eruption to prefer two directions and avoid a third. The star found it easy to throw its body out the top and the bottom, and hard to throw it out around the equator, and the shape we see is the frozen record of that preference. So the question the homunculus hands us is sharper than, why did it erupt? It is, why did it erupt this way, along an axis, instead of all at once in a ball? One way to break that symmetry is for the star to be spinning fast. A massive star rotating quickly is not a perfect sphere. It bulges outward at its equator and flattens at its poles, pulled into a slightly squashed shape by its own spin, the way a spinning ball of dough widens at its middle. And that squashing does something subtle to the star's light. On a rapidly spinning star, the flattened poles sit closer to the hot core and shine more fiercely, while the bulging equator sits farther out and runs cooler and dimmer. Since it is radiation pressure, the push of light, that drives material off a star this luminous, the poles push hardest. The brightest, hottest regions launch the strongest outflow, and so the star preferentially blows its material out along its spin axis, up and down, rather than around its slower, dimmer waist. spin the star, and the light itself funnels the eruption into two polar jets of gas. Another route to the same shape starts not with the star, but with what surrounds it. Suppose that before the eruption, a dense ring or disk of gas already sat around the star's equator, a thick belt of material encircling its middle. When the eruption fires, that belt acts like a wall. Gas trying to escape sideways runs straight into the dense ring and is choked off, while gas heading up and down finds open sky and rushes out freely. Picture blowing hard into a balloon that has a tight cord cinched around its center. The balloon cannot swell at the waist where the cord grips it, so it bulges above and below instead, and you get two rounded lobes with a pinch between them. That is the homunculus, and the equatorial belt is the cord. We even see hints of that belt today, a thin skirt of material lingering around the waist, the leftover of whatever channeled the blast. Whatever did the shaping, notice what the shape is telling us about the star underneath. A perfectly symmetric star, sitting alone, with nothing spinning it fast and nothing wrapped around its equator, has no reason to erupt along an axis. For the eruption to come out as an hourglass, something had to impose a direction on it, a top and a bottom and a forbidden middle. The star was not a lonely, featureless ball when it blew. It had structure, an axis, a plane it respected, and it carried that hidden geometry with it into the eruption and stamped it onto the debris. The homunculus is not just wreckage, it is a cast of the star's own hidden symmetry, taken at the moment it lost control. We can do far more than admire that shape, though, because the whole thing is still moving, and we can measure the motion. The lobes are not frozen. They are rushing outward right now, the near cap coming toward us and the far cap racing away. And by reading how that gas shifts the wavelengths of its own light, we clock the expansion at hundreds of kilometers a second, with some knots moving faster still. At those speeds, the whole structure has grown large enough that its two lobes now span close to a light year from tip to tip. That is the wreckage of one star's outburst, and it is already nearly a quarter of the way to the distance between our sun and its nearest neighbor. A single convulsion of a single star, blown out into a cloud almost as wide as the gap between stars. And because it is expanding, we can run the film backward. If we know how fast every part of the homunculus is moving outward, and how far out each part has traveled, we can rewind that motion, shrinking the lobes back toward the center, to ask when all of this material was sitting at the star, about to be thrown. When we do that arithmetic, the expanding gas converges back to a single moment, and that moment lands squarely in the middle of the 1800s. The debris itself, simply by flying apart at a measured speed, points its own finger back at the 1840s. We did not have to trust old brightness records to tie this cloud to the Great Eruption. The cloud told us its own birthday, and the date it names is the same one the sky watchers wrote down. The material inside those lobes carries one more confession, and it goes deeper than shape or motion. When we read what the gas is made of, we find it unusually rich in nitrogen and starved of carbon and oxygen. That specific imbalance is a fingerprint of nuclear processing, the signature of gas that has been down inside a star's fusion furnace and cooked by the reactions that run there. So the homunculus is not made of ordinary surface gas the star happened to shrug off. It is built from material dredged up from deep inside, from layers that had already been transformed in the star's interior, then hurled out into the open. When we look at these lobes, we are looking at the star's own processed insides turned out into space, the deep body of Eta Carinae laid bare. Something enforced an equator on this eruption. Something gave the star an axis to blow along and a plane to avoid. Whether by spinning it or by wrapping a dense belt around its middle, or both. But an axis and an equatorial plane are exactly what you get from an orbit. A single, isolated star has no particular reason to define a special plane in space. Two stars circling each other define one automatically, the flat plane of their mutual orbit. So when we stare into the narrow waist of the homunculus, we may not be looking at one star that happened to spin. We may be looking at the plane of a dance, and the sharpest question the shape leaves us is simple. What if the thing sitting at the center of this hourglass was never one star at all, but two? The shape gave us a suspicion, but a suspicion is not a discovery, and for a long time, that is all we had. An hourglass has an axis, and an axis hints at an orbit, yet the wreckage alone could never prove a second star was there. A single spinning star could, in principle, carve two lobes on its own. So if we wanted to know whether Eta Carinae was one star or two, we could not settle it by staring at the cloud. We had to catch the second star in the act of being there. And that is much harder than it sounds, because we cannot see it. Start with why we cannot simply look and count. Even in our sharpest images, Eta Carinae is a single smear of light. If two stars are circling each other from 7,600 light-years away, and at their closest they sit only as far apart as Mars sits from our own sun, then the gap between them, seen from here, is impossibly tight. It is like trying to tell, from one city away, whether a distant streetlight is one bulb or two bulbs held a hand's width apart. The light blurs together into a single point long before you can split it. On top of that, the star that matters most is buried in its own dust, the thick shroud of the homunculus, so even the brighter of the pair is half hidden from us. We were never going to find the companion by resolving two dots. We had to find it by its close effects. The first effect we noticed was a rhythm, and rhythm is a strange thing to find in a star like this one. When we watched Eta Carinae carefully over years, we saw that it does not just flicker at random. Certain features in its light rise and fall on a repeating cycle, and that cycle is astonishingly regular. Every 5.5 years, almost to the season, the star runs through the same sequence of changes and comes back to where it began. Now, a lone massive star at the edge of stability has no reason to keep a clock. Its surface churns, its wind gusts, its brightness wanders, but none of that should repeat on a fixed schedule you could mark on a calendar. Precise, repeating timing is the signature of an orbit, because an orbit is the one thing in a star's life that comes back around on a fixed period. When we see something happening like clockwork every 5.5 years, the clock is almost always two bodies swinging around each other. The clearest tick of that clock is something we can watch switch off and on. In the light of Eta Carinae, there are certain emission lines that require very high energy radiation to produce, the kind of hard ultraviolet light that the cooler main star cannot supply on its own. For most of the 5.5-year cycle, those high energy lines are there, glowing steadily. Then, on schedule, they fade and disappear for a matter of weeks, and afterward they slowly return. Something is periodically shutting off a source of intense ultraviolet light and then letting it back on. A single star does not do that. But a hot companion on a stretched orbit does exactly that. When it swings in close and plunges through the dense wind of the larger star, letting that thick gas smother its ultraviolet glow for a while before it climbs back at her. Those vanishing lines are the companion ducking behind a curtain of the primary's own wind, once every orbit. The evidence that finally nailed it came from the most violent light of all. When we look at Eta Carinae in X-rays, We see a source that brightens as the two stars approach each other, climbs to a sharp peak, and then crashes down into a deep minimum right at their closest pass, before slowly recovering. That pattern is not something a single star produces. X-rays this hard come from gas heated to tens of millions of degrees, and the natural way to heat gas that violently is to slam two powerful stellar winds into each other at high speed. The larger star drives a dense, heavy wind outward, and the companion drives a thinner, much faster one, and where those two streams collide, they shock and blaze in X-rays. As the stars draw closer, the collision grows fiercer and the X-rays brighten. At the very closest approach, the collision zone is buried so deep in dense gas that the X-rays are choked off and the light drops out. We are watching two winds crash together, and only two stars can make two winds. So we assembled the pair, piece by piece, without ever seeing the second one directly. At the center sits the monster we have been circling all along, a star of roughly 100 times the mass of our Sun, one of the most luminous stars in the entire galaxy, cool-surfaced for its size and wrapped in dust. And bound to it, demanded by every rhythm and every X-ray flare, is a companion we have never once seen as its own point of light. That hidden partner carries something like 30 times the Sun's mass, which would make it an enormous, blazing star in its own right anywhere else in the sky, the kind of star that would dominate its neighborhood alone. Here it is only the smaller of two, a fierce hot star riding shotgun to something far larger, close enough to be lost entirely in the glare of its companion. We know it is there the way you know someone is in a dark room, by the way. Everything else in the room responds to them. The orbit those two share is not the calm, near circle we might picture when we think of one star going around another. It is a stretched, lopsided ellipse, one of the most eccentric orbits known among massive stars. For most of the 5.5 years, the companion is far away, out near the distance at which Neptune circles our own Sun, drifting slowly through the cold outer reach of the system. Then it turns and falls inward, faster and faster, and at closest approach, it whips in to within roughly the distance between Mars and our Sun, skimming past the giant before being flung back out toward the cold again. Picture a long, narrow racetrack rather than a circle, where the smaller star coasts through the vast far turn for years and then screams through one brief, blistering pass close to the giant before the track carries it back out. Almost all the drama of this system is packed into that short, close passage, and then the pair spends years apart before doing it again. Back at the Homunculus, we wondered what could have imposed an equator on the eruption. Some plane the blast respected, some axis it blew along. Two stars locked in an orbit define a plane automatically, the flat sheet their motion traces out year after year. The pinched waist of the hourglass, the belt of gas around the middle, the two lobes reaching out along one axis, all of it lines up with the idea that a companion was already there, already carving a plane into the system, when the Great Eruption fired. The second star may not have merely witnessed the eruption, it may have helped shape it, its gravity and its orbit steering how and where the giant threw its body into space. A story we began as the tale of one unstable star keeps turning into the tale of two stars caught in a violent relationship. This is a system built on instability, a giant balanced against its own light, shedding its mass in convulsions, wrapped in the debris of a near-death eruption. Nothing about it should be orderly. Yet the two stars keep time so precisely that we can predict, years ahead, the exact season when the companion will make its next close pass and the X-rays will flare and fall. A dying, churning monster that nonetheless runs on a clock we can set our calendars by. So the question waiting for us is not whether they meet, but what happens when they do. What unfolds in that brief, furious, close passage once every 5.5 years, when the smaller star stops coasting and plunges straight into the wind of the giant? We can predict this star's next crisis the way we predict a tide. Somewhere in the coming years, on a date we can already circle, the companion will come screaming in toward the giant. The X-rays will spike and then collapse. The high-energy lines will vanish for a few weeks, and the whole system will convulse the way it has every 5.5 years for as long as we have watched it. We know this in advance. That is the part worth pausing on tonight, because everything else about Eta Carinae resists prediction. It is a star that could shed a chunk of itself without warning, that erupted once without any schedule we understand, that sits balanced on the edge of coming apart. And yet folded inside all that chaos is a clock so steady we can set our calendars by it. To feel how odd that pairing is, think about what usually keeps good time in nature. Regular rhythms tend to come from calm, simple systems. A pendulum swings evenly because nothing is disturbing it. The seasons return on schedule because the Earth's orbit is smooth and undramatic. Precision, in most of the physical world, is a sign that a system has settled into an easy, repeating groove. Eta Carinae has settled into nothing. Its surface heaves, its wind gusts and stalls. Its brightness wanders in ways we still cannot fully account for. By every measure of its own behavior, this is a system in turmoil. So when we find a metronome buried inside that turmoil, ticking off 5.5 years with almost stubborn accuracy, we are looking at something that should not be able to keep time, keeping it anyway. The reason it can is that the clock is not coming from the star's chaos at all. It is coming from the one thing in the system that gravity holds to an exact schedule, the orbit itself. Two bodies bound together trace the same path over and over, and the time it takes to complete one loop does not care how violent the stars are, how wild their winds, how unstable their surfaces. The orbital period is set by just two things: how much mass the two stars carry between them and how far apart they swing. Those quantities barely change from one loop to the next, so the period barely changes either. The stars can rage all they want inside that orbit. The orbit keeps its own time regardless, indifferent to the storm it is carrying. On this stretched, lopsided orbit, there is a single instant each cycle when the companion reaches its closest approach to the giant, the point we call periastron. Everything dramatic in the system is triggered by that approach. As the smaller star falls inward, the collision between the two winds intensifies and the X-rays climb. Then, right at closest approach, the companion buries itself so deep in the dense wind of the giant that the X-ray glow is smothered and drops into a sharp minimum, the deep dropout we can time to within days. The high-energy emission lines fade in the same passage, choked off as the hot companion plunges behind that thick curtain of gas. None of these events wander, because the geometry that causes them does not wander. They are locked to the moment of closest approach, and closest approach is locked to the orbit. There is a real payoff to that reliability. Because these events arrive on schedule, we can prepare for them. When we know years ahead exactly when the next periastron will fall, we can arrange for our telescopes, our X-ray observatories, our whole scattered fleet of instruments to be watching at the same time, aimed at the same star, during the few precious weeks when it does its most revealing work. Most of astronomy is the study of things that happen whenever they happen, with no regard for whether anyone is looking. Eta Carinae hands us the rarest gift a violent object can give: a recurring appointment. We do not have to wait and hope to catch it in the act. We know the date, and we can be ready, cycle after cycle, building up a record of the same event seen again and again. And each time we keep that appointment, the clock itself becomes a measuring tool. A perfectly steady period would tell us the orbit is unchanging. But if the period drifts, even slightly, that drift carries information. When two stars pour off as much mass as these do and slam their winds together this hard, the orbit does not stay perfectly fixed forever. Mass leaving the system and the friction of those colliding winds can nudge the star's path over time, and a nudge to the orbit shows up as a tiny change in the timing. So by watching whether the 5.5-year beat holds exactly or slips by days across many cycles, we can read the slow evolution of the orbit itself, the gradual shifting of two stars we cannot even see as separate points. The clock does not just tell us when. Watched closely enough, it tells us how the dance is slowly changing. Let yourself hear the strangeness in that once more, because it sits at the heart of what this star is. We opened all of this with a monster balanced against its own light, a star so luminous it can barely hold itself together, wrapped in the wreckage of an eruption we still cannot fully explain. Nothing about that picture suggests order. Yet here we are, able to say with confidence that on a particular date, still years away, this unstable giant and its hidden companion will reach their closest pass, and the whole system will flare and fall exactly as it did the time before. Chaos on the surface, order in the orbit, a furnace that cannot keep its own shape, riding a clock that never misses. The instability and the precision are not in conflict. They live in different parts of the system, the chaos in the stars, the timekeeping and the gravity that binds them. That steadiness carries us to the edge of something we have been circling from a distance all along. We have been talking about periastron as a moment on a clock, a date to mark, and a signal to catch. But for the two stars, it is not a mark on a calendar. It is a physical event, a real and violent encounter that happens when the smaller star stops coasting through the cold far reach of its orbit and plunges inward. Twin winds, one heavy and slow, one thin and blistering fast, are driven straight into each other at that closest pass, harder than at any other point in the cycle. We have named the schedule. We have not yet stood inside the collision. So the question that pulls us forward is what actually happens in that crash, in the narrow zone where two stellar winds meet and neither one yields. Every star that shines this fiercely is also leaking itself away. We tend to think of a star as a fixed ball of fire, but a luminous star is more like something slowly boiling off its own surface. The same radiation pressure that nearly tears the giant apart also lifts gas off the top of it continuously, driving a steady outward stream of material into space. We call that stream a stellar wind, and for a star like the giant in Eta Carinae, it is a monster in its own right. The sun sheds a thin, gentle breeze of particles, so faint it would take it well over 10 million years to lose a single sun's worth of mass. The giant here sheds its wind so heavily that it can lose that same amount in mere thousands of years, a gale thousands of times denser than anything our own star produces. Now remember that there are two stars, and each drives a wind of its own. The giant pushes out a wind that is thick and heavy, but relatively slow, a dense flood of gas moving at several hundred kilometers a second. The companion, smaller but far hotter, drives a wind that is thinner but blistering fast, racing outward several times quicker than the giant's. Two winds, then, with opposite personalities. One is a slow, crushing tide of material. The other is a lean, high-speed jet. And because the two stars are bound in orbit, these winds are not blowing off into separate corners of space. They are aimed straight into each other, meeting somewhere in the gap between the two stars, and neither one is willing to give way. Picture what has to happen where they meet. Two streams of gas, each moving at hundreds or thousands of kilometers a second, run headlong into one another and cannot simply pass through. Gas is not like light, where two beams cross and continue untouched. Gas is made of particles, and when two dense streams of particles slam together, they pile up, compress, and stall against each other, forming a wall of shocked material trapped between the two stars. Where exactly that wall sits depends on which wind pushes harder. The giant's wind is heavier, so it tends to shove the collision zone toward the companion, backing the smaller star into a corner, its thin, fast wind carving only a narrow cavity against the giant's overwhelming flood. The two winds find a balance point, a curved front where their pressures match, and that front is where the violence happens. What makes that collision matter is what it does to the temperature. When gas moving that fast is suddenly stopped, its energy of motion has to go somewhere, and it converts almost entirely into heat. This is the same physics you feel when you pump up a bicycle tire, and the pump grows warm in your hands, the gas heating as it is compressed and its motion is halted, just carried to an extreme we have no everyday experience of. Here, the streams are not moving at the pace of a bicycle pump. They are moving at a fair fraction of a percent of the speed of light. When motion that violent is arrested in the collision front, the gas is heated not to hundreds of degrees, not to thousands, but to tens of millions of degrees. The zone between these two stars becomes one of the hotter places in this whole region of the galaxy. Not because of fusion, not because of any nuclear fire, but purely because two winds crashed and their speed became heat. Gas that hot does not glow in ordinary light. A campfire glows red, hotter metal glows orange and then white, and the surfaces of stars glow in visible colors because they sit at a few thousand degrees is less than. But push a gas to tens of millions of degrees and it radiates at a far higher energy, in X-rays, a form of light our eyes cannot see and our atmosphere does not even let through to the ground. This is why so much of what we know about the collision came only after we could put X-ray telescopes above the atmosphere and look at Eta Carinae in that light. In visible light, the collision hides inside the glare of the stars and the dust. In X-rays, it stands out sharply, a compact, blazing knot of gas sitting between the two stars, marking the exact place where the winds meet and die against each other. And because the orbit is so stretched, that collision is never the same twice. When the two stars are far apart, out in the long, cold stretch of the orbit, the winds meet gently, spread thin over the great distance between them, and the X-ray glow is steady and moderate. As the companion falls inward toward its close pass, the two stars crowd together, the winds collide closer to their sources where they are denser and fiercer, and the collision front is squeezed into a smaller, hotter, brighter knot. The X-rays climb as the stars approach, brightening month by month, tracking the shrinking distance between them. We are, in effect, watching a thermometer respond to two stars falling toward each other, the heat of their meeting rising in step with how close they have come. Then, at the closest approach, the pattern breaks in a way that took us years to understand. Just when the collision should be at its most brilliant, the X-rays do not peak and hold. They spike, and then they crash, dropping into a deep minimum that lasts for weeks before slowly climbing back. At first, that seems backward. The stars are closest, the winds are fiercest, the collision should be at its hottest, and yet the X-ray light nearly vanishes. The resolution is that at closest approach, the companion plunges so deeply into the dense inner wind of the giant that the whole collision zone is buried under a thick blanket of gas. The X-rays are still being produced, but they are smothered before they can escape to us, absorbed by the very material crowding around the collision. The light does not disappear because the collision stops. It disappears because it gets trapped. There may be more than smothering at work in that dropout, and this is where we should be careful about how much we claim. Some evidence suggests that during the closest, most crushing part of the passage, the giant's heavy wind can briefly overwhelm the companion's wind so completely that the smaller star's outflow is nearly snuffed out, the collision itself faltering for a time before recovering as the stars separate again. Whether the deep minimum is mostly a matter of the X-rays being absorbed, or partly the collision truly collapsing and rebuilding, is still something we are working to pin down. What we can say plainly is that this is not a quiet system finding equilibrium. It is two winds locked in a contest that intensifies, breaks, and reforms with every orbit, never settling, never resolving. Step back and hold the whole scene in view, because the collision is stranger than just a hot spot between two stars. This wind collision is doing something that, on Earth, we can only achieve inside our most sophisticated machines. It is taking ordinary gas and, through the raw physics of speed, meeting resistance, heating, and energizing it to extraordinary states, again and again, on a repeating cycle. We built enormous facilities to accelerate and collide particles to reach conditions of extreme energy, and here is a system doing something with a distant kinship to that on a scale no laboratory could ever match, powered by nothing but two stars and their unwillingness to yield to each other. The collision front is not the end of this story. It is the doorway to it. Because when gas is shocked this violently, it does not only grow hot and pour out X-rays. Something begins happening to individual particles in that front, something that turns this stellar crash into one of the most powerful natural engines we have found anywhere near us. We left the collision as a wall of gas heated to tens of millions of degrees, pouring out X-rays. But heat is a crowd phenomenon. When we call a gas hot, we are describing the average jostling of countless particles, all bumping into one another and sharing their energy in a rough democracy where no single particle gets to keep much more than its neighbors. What happens next in this front is a different kind of thing entirely, because it stops being about the crowd and starts being about a lucky few. A small fraction of the particles caught in that shocked gas do not simply grow hot along with everyone else. They get singled out, seized, and driven to energies the rest of the crowd never approaches. By the time the front is finished with them, these few are no longer moving at the pace of hot gas at all. They are moving at nearly the speed of light. To see how a plane collision between two winds can do that, we have to look at what a shock front actually is up close. It is not a solid wall. It is a boundary where fast gas slams into slower gas, and threaded all through it are tangled, knotted magnetic fields, carried along and twisted up by the churning plasma. Now imagine a single charged particle wandering into that region. It does not pass straight through. The magnetic tangles deflect it, bouncing it back and forth across the boundary, sending it from the fast side to the slow side and back again, over and over. Here is the part that matters. Each time the particle crosses the front, the gas on the far side is rushing toward it, and the particle bounces off that oncoming flow like a ball struck by a moving paddle instead of a still one. A ball thrown against a wall comes back with the speed it arrived. A ball met by a paddle swinging toward it comes back faster. Cross the shock once, and the particle gains a little speed. Cross it 1,000 times, bouncing between two flows that are always moving toward each other, and those tiny gains compound into something enormous. This process has been understood for decades, And it is the same mechanism we believe fills our whole galaxy with high-energy particles. The particle keeps bouncing until, eventually, it either escapes the region or reaches such a blistering energy that the shock can no longer hold on to it. A few unlucky, or lucky, particles ride that cycle so many times that they leave the front carrying millions of times the energy they came in with, accelerated not by any machine, but by the simple geometry of two flows converging and a magnetic field that will not let a particle sit still. We usually find this happening in the shredded, expanding debris of stars that have already died. To find it running inside a system of two stars that are both still alive, powered by nothing but their winds refusing to yield to each other, is far less common, and it makes Eta Carinae something rare and valuable to us. Once particles reach those speeds, they announce themselves in a way we can catch across the whole distance to Earth. A charged particle moving at nearly light speed does not stay quiet. When it whips through a magnetic field or brushes past the light streaming off the two stars, it radiates, and it radiates at the very top of the energy scale, in gamma rays. Gamma rays are light, the same fundamental thing as the glow of the lamp near you, but they sit at the far violent end of the spectrum, far beyond visible colors, far beyond even the X-rays from the wind collision. There are two ways the fast particles make them here, and both are running at once. The fast-moving electrons collide with the ordinary, low-energy light of the stars and kick those gentle photons up to gamma energies, like a fast bat sending a softly tossed ball screaming off at tremendous speed. And the fast protons crash into the gas of the wind itself, and those crashes spit out tiny, short-lived particles that decay almost instantly into gamma rays. Either way, the message that reaches us is the same. Somewhere in that system, matter is being driven to energies we associate with the most extreme places in the universe. The energies involved are hard to hold in the mind, so let us anchor them. The particles of visible light landing on your skin right now each carry a modest sip of energy, a couple of electron volts apiece, the ordinary currency of chemistry and warmth. The gamma rays we have caught coming from Eta Carinae carry up to a few 100 billion electron volts, each single one of them. Try to feel the size of that jump. A single one of these gamma photons packs the energy of something like 100 billion particles of ordinary light, all bundled into one indivisible flash. One photon, carrying what 100 billion photons of lamplight would carry between them. That is the difference between the light warming your hand and the light this collision is flinging out into the dark. Catching that light took two very different kinds of eyes, and the deeper energies took the stranger method. The lower reaches of this gamma glow were first picked up by a telescope above the atmosphere, tuned to see gamma light directly, which found a steady source sitting exactly where the two winds meet. But the highest energies, those few 100 billion electron-volt photons, are so rare that we catch them from the ground, and we do it by watching the sky itself flinch. When one of these gamma rays strikes the top of our atmosphere, it shatters into a cascade of particles that briefly travel faster than light does through air, and that burst leaves a faint blue flash, lasting a few billionths of a second, high overhead. We build wide mirrors on dark mountainsides to catch those tiny flashes, and from them we reconstruct the gamma ray that made them. So, the very same collision we cannot see with our eyes, buried in dust and glare 7,600 light-years off, is writing its signature onto our own upper air, one faint flicker at a time, and we have learned to read it. There is a reason we push so hard to measure the very highest energies, and it comes down to a distinction we cannot draw any other way. Light made by fast electrons and light made by fast protons look nearly identical at lower energies, but near the top of the scale they finally diverge, and only the proton path tells us that actual matter whole nuclei, is being driven to these extremes, rather than just feather-light electrons. Protons accelerated this violently are the raw ingredient of what we call cosmic rays, the high-energy matter that drifts through the entire galaxy. So reaching those few 100 billion electron-volt photons is how we test whether this system is merely glowing or truly building that matter and readying it to send outward. And this accelerator does not run at a constant setting. Remember the stretched orbit, the 5.5-year clock, the close pass that squeezes the wind collision into its fiercest, most compressed state. The particle acceleration answers to that same clock. As the two stars fall toward each other, the shock grows stronger and denser, the acceleration sharpens, and the high-energy light responds, shifting and changing across the orbit rather than holding steady. So the natural accelerator sitting at the heart of this system has a throttle, and the throttle is the orbit itself. Every 5.5 years, as the companion swings in and the winds crash hardest, the whole engine is pressed toward its peak, and then it eases as the stars draw apart again. The clock we found in the light, and the heat we found in the X-rays, and the raw particle physics we are describing now are all the same events seen at different energies, all governed by the same two stars and the same relentless orbit. The gamma rays reach us as light, and light travels in a straight line, which is why we can point back along that line and say the glow comes from Eta Carinae. But the fast protons and nuclei, the particles themselves, are not bound to stay in the system that made them. Once accelerated, many of them break free of the collision zone entirely and drift outward, escaping the two stars and wandering off into the wider galaxy as free, high-energy particles. They leave the accelerator behind and begin a long, slow journey through interstellar space, no longer tied to the star that flung them. Which forces a question we have not dared to ask yet. If this system is throwing particles out into the galaxy at nearly the speed of light, and has been doing it for a very long time, then where do those particles go? And is there any chance that some of them, eventually, arrive here? Follow one of those escaping particles, and you might expect a clean, straight flight out into the galaxy. A proton leaves the collision zone at nearly the speed of light, and light goes in straight lines, so surely the particle does too. It does not. The moment that proton leaves the system, it enters a galaxy that is not empty space at all, but a vast volume threaded everywhere with magnetic fields. They are faint, far weaker than the field of the small magnet holding a note to your refrigerator, but they fill the entire galaxy and stretch across thousands of light years without a break. And a charged particle cannot move straight through a magnetic field. It is forced to curve, to wind around the field lines, to spiral along them instead of cutting across. So our proton does not fly out of the galaxy like a bullet. It begins to wander. Picture trying to walk in a straight line through a thick fog-bound forest in the dark. You mean to go due north, but you cannot see, and every few steps you glance off a trunk you never saw coming and get turned a little. Step by step, deflection by deflection, you do drift somewhere, and after long enough you end up far from where you began. But if someone found you at the end and asked which direction you had come from, you could not tell them, and neither could they reconstruct it from where you stand. The path erased its own memory. That is what the galaxy's tangled magnetic field does to a cosmic ray. It scatters the particle this way and that, so many times over, so long a journey, that by the time the particle arrives anywhere, the direction it came in from tells you nothing about where it was born. The time this random walk takes is its own kind of staggering. If a particle could travel straight from Eta Carinae to us, the trip would take the same 7,600 years the light takes, since both move at nearly the same speed. But a cosmic ray does not travel straight. It ricochets through the magnetic maze, doubling back, looping, wandering, covering a tangled path enormously longer than the direct one. A particle that could have crossed a good stretch of the galaxy in 100,000 years, moving straight, can instead spend millions of years bouncing around inside it before it finally drifts out or reaches us. So these particles are not just anonymous about their direction, they are ancient. The cosmic rays washing over us now may have been launched by their sources long before there were human beings here to build the instruments that catch them. Put those two facts together, and something important follows for our whole question. If every cosmic ray arrives scrambled in direction and smeared across millions of years, then the particles reaching Earth do not come at us from any one point in the sky. They come from everywhere, roughly evenly, a steady rain falling on our planet from all directions at once, because their true origins have been stirred into a common pool. And that is exactly what we measure. The cosmic rays striking Earth arrive almost perfectly evenly across the sky, with no bright spot marking any single source, which leaves us in a frustrating and honest position. We cannot catch a cosmic ray, trace it back, and declare that this one came from Eta Carinae. The particle simply does not carry a return address anymore. The galaxy took it. This is the real reason the gamma rays matter so much to us, and why we spent so long on them. The gamma rays are our proof, precisely because they are not charged. Being pure light, they ignore the magnetic maze entirely and travel straight to us, still pointing back at the exact spot where they were made. So the gamma rays let us stand at this distance and say, with confidence, that particles are being accelerated to tremendous energies inside that system, right there, at that point on the sky. The escaping matter is the part we lose track of. We can prove the accelerator is running by the straight light it emits, and we can reason that it must be feeding particles into the galaxy, even though we can never fingerprint a single one of those particles after it leaves. We see the muzzle flash clearly. We just cannot follow any individual round once it is loose in the dark. At the very highest energies cosmic rays can reach, energies far beyond anything a system like Eta Carinae produces, the particles are moving with so much momentum that even the galaxy's magnetic field can barely bend them, and those rare, ultra-energetic particles do fly nearly straight. But those extreme cosmic rays are thought to come from violent events far outside our galaxy, not from two stars in our own neighborhood. The particles that Eta Carinae accelerates sit at more modest energies, well inside the range that the magnetic field scrambles thoroughly. So for this star, specifically, the honest statement is the humble one. It is very likely feeding particles into the galactic sea, one more contributor among many to the cosmic rays that drift through our region, but not a source we can ever point to and confirm from a single arriving particle. If we add up the energy carried by all the cosmic rays drifting through interstellar space and set it beside the energy in the starlight that fills the galaxy, and beside the energy stored in those pervasive magnetic fields, the three come out roughly equal. The cosmic rays are not a faint trace riding along in the background. Spread through the vast volume of the galaxy, they hold about as much energy as all the starlight does, and as all the magnetic fields do. They are one of the great reservoirs of the galaxy, a permanent, pervasive part of what interstellar space is made of, continuously refilled by accelerators like the one running at the heart of Eta Carinae. Now let this settle into something you can feel, because it changes what the distance to this star even means. Cosmic rays are not an abstraction happening far away in space. They are falling on you continuously, right now, tonight. When one of these high-energy particles strikes the top of our atmosphere, it smashes into an air molecule and shatters into a spray of new particles, which strike more molecules and spray again, a cascade raining down through the sky. Some of those particles reach all the way to the ground, and they pass through the roof above you, through the room, through your own body, several of them slipping through you every second of your life without your ever noticing. You have never once felt them. They have been passing through you since before you were born, and through every living thing that has ever existed on this planet. And a share of that endless, gentle rain traces back to accelerators like the one we have been describing. Not to Eta Carinae alone, and never to a particle we could label, but to the whole population of violent sources across the galaxy that fling matter to these speeds, of which this colliding wind system is one working example we can actually watch. So think again about what distance has meant across this story. The light of Eta Carinae reaches us as a clean, straight beam from one point in the sky, old and directional, arriving with a date stamped on it. Its matter reaches us in the opposite way, stripped of direction, stripped of time, mixed into a sea that falls on us from every side and drifts through our bodies unremarked. The star is 7,600 light-years away by the ruler of light. By the reckoning of its particles, it is not entirely out there at all. Some faint part of what such stars produce is already here, in the air, in the ground, in us. That is a strange place to have arrived, starting from a simple question about how far away a star is. We began by trying to measure a gap, and we have ended up finding that the gap is crossed constantly, by light on one path and by matter on another, one arriving as news and the other as anonymous, ancient rain. But notice what we have quietly assumed through all of it. We have been telling this as the story of two stars, a giant and its hidden companion, driving two winds into each other. That picture explains the clock, the X-rays, the accelerator, the particles. What it has never fully explained is the thing that started everything, the Great Eruption itself, that convulsion too fast and too cool to be a simple wind. And when we look hard at what it would take to produce that, two stars quietly orbiting may not be enough. The origin of this whole system may demand something more violent than an orbit, and that is where we have to turn next. We have a good account of how Eta Carinae sheds mass in general. A star balanced against its own light, pushed past the edge where radiation wins, can drive material off itself in enormous quantities. That explains a heavy wind, even a severe one. What it strains to explain is the Great Eruption in full. Not just that the star lost more than 10 times the mass of our Sun, but that it did so while flinging some of that material outward at thousands of kilometers a second, at speeds we associate with an explosion, and released, in total, energy approaching that of a real stellar detonation. A star gently overflowing its limit does not do that. Overflowing is a leak. What we see in the wreckage looks less like a leak and more like a blast. What could release the energy of an explosion, throw matter at explosive speed, and still leave a living star behind afterward? A single star has only so many ways to do violence to itself, and none of them fit cleanly. But there is another source of sudden, enormous energy in the cosmos that does not require destroying a star at all, and it comes not from one star, but from two. The growing suspicion among the people who study this system is that the Great Eruption may not have been a star convulsing on its own. It may have been two stars colliding and becoming one. Think about what it takes for two stars to merge and where the energy comes from. When two stars orbit each other and slowly spiral inward, they are falling, in the plainest sense of the word, deeper and deeper into each other's gravity. Anything that falls releases energy, the same way a rock dropped from a height arrives at the ground carrying the energy of its fall. Two stars spiraling together are falling an enormous distance, carrying an enormous amount of mass, and when they finally meet and coalesce, all of that gathered energy of falling has to be released in a short span of time. The outer layers of the two stars, crashing together and unable to simply merge quietly, get flung outward in a violent burst. A stellar merger, then, is a way to unleash something like the power of an explosion, driven purely by gravity and motion, that ends not with a destroyed star but with a single, larger, more massive one standing where two used to be. Remember the strange material we read in the light echoes, gas moving at close to 10,000 kilometers a second, far too fast for any wind. A merger accounts for that easily. The collision of two stars can launch debris at exactly those explosive speeds, while a star merely shedding its skin cannot. Remember, too, the sheer energy of the event, close to that of a true stellar detonation. The gravitational energy released when two massive stars fall together and merge is more than enough to power an eruption on that scale, without ever needing the star to actually blow itself apart. The very thing that made the eruption so hard to explain, its explosive character in a star that survived, is the natural fingerprint of a merger. There is a deeper reason the speed alone points away from a wind, and it comes down to where the energy is released. Gas driven off the surface of a star leaves at roughly the speed it would need to escape that surface, and for a bloated giant, that escape speed is only a few hundred kilometers a second. To fling material 10 or 20 times faster than that, you cannot lift it gently off the swollen outer skin of the star. You have to release the energy far deeper, closer to the compact core where gravity is fierce and the speed needed to escape is enormous. A merger does precisely that. When two stars plunge together, the energy is unleashed deep down, in the tight, high-gravity region where matter can be hurled outward at the very speeds we actually measure in the echoes. A wind starts at the surface and leaves slowly. The eruption started somewhere much deeper, and that depth is itself a mark of a collision. The idea reaches even further, into the shape and the spin we puzzled over earlier. When two stars merge, they do not just add their masses together, they pool their motion. Two bodies that were whirling around each other pour all of that orbital spin into the single star they become, and the result is a new star turning far faster than either of the originals. Cast your mind back to the hourglass, and to the reason we suspected a fast spin in the first place, the way a rapidly rotating star funnels its eruption along its poles. A merger delivers exactly that fast spin, for free, as a consequence of the collision. And it delivers something else we have been circling since the beginning. Merging two large stars into one produces a single star more massive than either parent, more luminous, and pushed harder against the Eddington limit, the very edge of self-destruction we described. The monster we see, spinning fast, blazing near its own breaking point, balanced against its own light, is precisely the kind of star a violent merger would leave behind. Let yourself feel what this would mean about the thing we have been calling a star. Through this entire account, we have spoken of Eta Carinae as one object with a companion, a giant with a smaller partner circling it. If the merger picture is right, then the giant at the center is not a star in the ordinary sense at all. It is the survivor of a collision, the fused body of two stars that spiraled together and became one, still unsettled from the violence of its own making, still shedding the aftermath of it into space. The point of light we named, catalogued, and studied for centuries would be a wound that has not finished closing. Not a star having a bad century, but the scar left where two stars used to be. No one watched two stars merge inside Eta Carinae. We are reasoning backward from the wreckage, asking what kind of event could have left behind the eruption we can measure, the eccentric orbit we can time, the fast spin we infer, the explosive debris we can read in the echoes. The merger hypothesis fits those clues more comfortably than a lone star straining against its own light does, and that is why it has gained ground. But fitting the clues is not the same as being proven, and there are pieces that still resist the clean version of the story. The star did not erupt only once. There is evidence of earlier, smaller outbursts, and of material thrown off long before the Great Eruption of the 1840s, shells of gas that were already old when the Great Convulsion happened. A merger is, by its nature, a single event. It happens once. A star that has convulsed more than once, over centuries, is not something a lone collision explains all by itself, and honesty requires us to keep that tension in view rather than smoothing it away. So we sit with a picture that is powerful and incomplete at the same time. The best current thinking is that the heart of Eta Carinae is very likely a merger remnant, that the 1840s event was probably the moment two stars finished becoming one, and that this is the most natural way to explain the violence we see. Probably, very likely, not certainly. These are the honest words, and a curious mind should prefer them to false confidence, because the questions they leave open are more interesting than any tidy answer would be. And the biggest open question follows straight from the idea itself. Because a merger cannot happen on its own. Two stars in a stable orbit do not simply decide to spiral together. Left alone, they will circle each other quietly for ages, never touching. Something has to push them together. Something has to bleed energy out of their orbit and drive them inward until they collide. And one of the most reliable ways in nature to destabilize a pair of stars and force them to merge is to add a third star to the system, a third body whose gravity stirs the whole arrangement into chaos. We have been counting the stars in Eta Carinae, and we keep arriving at 2. The merger idea quietly insists there were once 3. So the question we carry into what comes next is simple to ask and strange to sit with. Where did the third star go, and what did it do to the other 2 before it left them changed forever? The third star was probably not a stranger that wandered in. When we find massive stars in the galaxy, we almost never find them alone. They are born in groups, and the heaviest of them tend to come in 2s and 3s, bound together from birth. So the most natural picture of Eta Carinae's origin is not a lone giant with a companion, but a family of 3, formed together out of the same collapsing cloud. 2 of them likely started as a close inner pair, orbiting each other tightly, while the third circled the pair from farther out, a wider, slower partner holding the whole arrangement together. An arrangement like that has a name, a hierarchical triple, and under most conditions it is perfectly stable. The inner 2 dance close, the outer one keeps its distance, and nothing dramatic ever happens. Most conditions, not all. The trouble begins when the outer star's orbit is steeply tilted compared to the plane of the inner pair. You might expect a distant third star, just circling quietly far away, to have almost no effect on the tight inner binary. Its pull is gentle, and it never comes close. But gentle does not mean harmless, because the effect we are about to describe does not depend on strength, it depends on patience. A tilted outer star tugs on the inner pair slightly unevenly through each of its long orbits, and although any single tug is tiny, the tugs do not cancel out. They accumulate, always in the same direction, orbit after orbit after orbit. Over thousands of years, those patient, repeating nudges slowly reshape the inner orbit, and they reshape it in one particular, dangerous way. What they do is trade the shape of the inner orbit for its tilt, back and forth, in a slow exchange. As the inner pair's orbit is pulled more upright relative to the outer star, it is also stretched, growing more and more elongated, less like a circle and more like a long, thin ellipse. This slow, driven stretching is called the Kozai leadoff mechanism, and the easiest way to feel it is to think of a child on a swing. One small push does almost nothing, but small pushes delivered at just the right point in each swing, over and over, build the arc higher and higher until the child is soaring. The outer star pushes the inner orbit like that, in rhythm, and what climbs is not height but eccentricity, the stretch of the orbit. With each cycle, the inner two stars swing closer at their nearest approach, until an orbit that began comfortably wide is bringing them skimming past each other, almost touching, at the tight end of a long ellipse. There is a sharp condition hidden inside this, and it is part of what makes the mechanism so unsettling. The stretching does not happen for just any tilt. Below a certain angle between the inner and the outer orbits, the two nudge each other only mildly, and the inner pair stays safely round for as long as the stars live. But tilt the outer orbit past roughly 40 degrees, and the trade switches on. The eccentricity begins its steady climb, and the inner pair is set on the slow road to collision. So whether a triple like this lives out a quiet life, or destroys itself from the inside, may come down to almost nothing, to the angle at which the three stars happened to be arranged when they were born. A few degrees of tilt at the start, decided long ago in a collapsing cloud, and everything that followed was already leaning toward catastrophe. Once the two inner stars are passing that close, the endgame begins. At each near miss, they raise enormous tides on each other, great bulges of gas pulled up by each star's gravity, and those tides drag on the orbit like friction, stealing energy from it. Their outer layers may begin to touch and transfer between them. Every one of these effects bleeds energy out of the inner orbit, and an orbit that loses energy shrinks. So the inner pair spirals inward, the close passes growing closer still, the whole process feeding on itself, until there is no orbit left to shrink. The two inner stars meet, and they merge, pouring together in the violent coalescence we have been calling the Great Eruption. The family of three has, in a matter of a human lifetime or two, become a family of two, with a merged giant where the inner pair used to be. Now follow the energy, because it tells us exactly where the third star ends up. To shrink the inner orbit and force the merger, a great deal of energy had to be pulled out of the system's motion, and energy does not simply vanish. Much of it goes into the violence of the merger itself, but a share of it gets handed to the outer third star, kicking it onto a new orbit. And the orbit a star gets kicked into by an event like this is not a calm circle. It is stretched and eccentric, carrying the recoil of the catastrophe that reshaped the system. Look at what we actually see today. The surviving companion of Eta Carinae rides one of the most eccentric orbits known among massive stars, sweeping far out and then plunging close every 5.5 years. That extreme, lopsided orbit is not a curiosity. Seen this way, it is a scar, the frozen record of the kick the third star received when its two siblings fell together and died as separate stars. Sit with what that makes the companion, the hidden star we have only ever detected indirectly. We know it is there from the X-ray flares, from the high energy lines that vanish and return, from the clockwork of the 5.5-year cycle. We have never seen it as its own point of light. And in this reconstruction, that unseen star is not an innocent bystander to the eruption. It is the cause of it. Its patient, tilted gravity is what stretched the inner orbit, drove the two inner stars together, and forced the merger that lit up the 1840s sky. The star we cannot see is the one that pulled the trigger, and then survived to circle the wreckage of what it had done, on an orbit still carrying the recoil. Cause and survivor, the same body, hidden in the glare. If the eruption was a single merger, a one-time coalescence, then why does the star seem to have convulsed more than once, throwing off older shells of gas that predate the 1840s event? The triple picture offers a possible answer, though we should hold it loosely. A triple driven toward merger does not stay quiet until the final instant. As the inner orbit stretches and the stars begin their close passes, the system can grow violently unstable in the centuries beforehand, shedding mass in fits and lesser outbursts as it staggers toward the crisis. In that view, the older shells are the tremors before the main shock, the system convulsing as it destabilized, with the Great Eruption as the moment it finally gave way. It is a reasonable story, and parts of it have been modeled, but not every detail is settled, and we should not pretend the timeline is fully understood. It is not. We did not have to invent rare objects or bend any rules to build this history. Massive stars are usually born in multiples. Triples among them are common, and the slow orbital trade that drives an inner pair to merge is a well-studied piece of gravitational physics that plays out across the galaxy. What makes Eta Carinae extraordinary is not that these things happened, but that they seem to have happened recently, and near enough, and to stars massive enough that we caught the aftermath while it was still glowing and moving. We are looking at an ordinary kind of stellar catastrophe, frozen in the middle of unfolding, close enough to study in detail. We never saw three stars. We never watched the inner orbit stretch, never witnessed the merger, never observed the third star take its kick. We have inferred an entire violent family history, a cause, a collision, a survivor, from indirect traces, from the shape of debris, the speed of gas, the eccentricity of an orbit, the flicker of light we cannot fully resolve. It is a powerful reconstruction, and it may well be right, but it is a reconstruction, built from clues rather than witnessed. So it becomes fair and necessary to ask a harder question of ourselves. After everything we have claimed to know about this star tonight, how much do we truly know, and how much are we inferring from the edges of what our instruments can reach? We know the color of this star's light and what its gas is made of. We know it is unusually rich in nitrogen, the fingerprint of material dredged up from deep inside a star and processed by fusion. We know its 5.5-year rhythm to within days, well enough to predict the next close pass years ahead. We know how its X-rays climb and crash, how its high-energy lines vanish and return, how its gamma rays flicker across the orbit. We know the shape of the great hourglass around it, and we have watched that hourglass grow, measured its expansion, and rewound it to name the 1840s as the year of its birth. And we know, past any real doubt, that there are at least 2 stars in there now. None of that is guesswork. All of it is measured. When we say the giant carries roughly 100 times the mass of our Sun and the companion around 30, we are not reading those numbers off a scale. We are inferring them from how the stars move, how bright they are, how their winds behave, run through models of how stars of that kind work. The models are good, and the numbers are probably close. But they are conclusions drawn through a framework, not raw readings. And if the framework is off, the numbers drift with it. The same is true of the distance itself. When we say 7,600 light-years, give or take a few hundred, we are trusting a chain of reasoning about expanding gas and reddened light, not a direct measurement we can simply check. This layer is sturdy, but it rests on ground we built ourselves. And then there is the third layer, the truly open one, and we should name its contents plainly rather than blur them. We do not know the exact distance to better than a margin of many hundreds of light-years, maybe more. We do not know for certain what powered the Great Eruption. We do not know for sure whether a merger happened, whether there were once 3 stars, or how to fully reconcile the older shells with a single collision. And we do not know precisely when it will die. These are not small footnotes. They are some of the most basic questions you could ask about an object, and after 2 centuries of the closest study, they remain open. That could sound like failure. It is not. It is the honest shape of a hard problem, and the shape itself is something to understand. Because not all of these unknowns are the same kind of unknown, and telling them apart changes how we should feel about them. Some gaps are gaps in measurement. We know exactly what we would need to observe, we simply cannot observe it well enough yet. The distance is mostly this kind. Nothing about it is mysterious in principle. The problem is entirely practical. The star sits behind a thick, badly behaved veil of dust that reddens its light in ways we cannot fully correct. It is so bright it overwhelms instruments built for ordinary stars, and it flickers while we try to pin it down. Give us a clean enough method, a better ruler that does not care about dust or brightness, and the number would snap into focus. This gap is waiting on tools, not on ideas. One of our best ways to measure the distance was to watch the 2 lobes of the hourglass expand and assume they were growing symmetrically, evenly in all directions. That symmetry was the whole trick that let the nebula measure its own distance. But look at what the merger story does to that assumption. If a violent collision shaped this eruption, then the material was flung out by a chaotic, lopsided event, and the neat symmetry we leaned on becomes exactly the thing we can no longer take for granted. So the more we learn about what this object truly is, the shakier one of our best tools for measuring how far away it is becomes. The plainest question in the whole story, its distance, is held hostage by the deepest one, its nature. We cannot fully nail down how far it is until we understand what it is, and we do not yet understand what it is. The eruption mechanism is a different kind of gap altogether. That one may not be waiting on a better telescope at all. It may be waiting on better understanding. We are still working out the physics of how the most massive stars behave when they are pushed to their limits, how they shed mass, how they merge, what happens in the extreme conditions of a stellar collision. It is possible that when we finally explain the Great Eruption, we will need a piece of physics we have not fully worked out yet, not just a sharper image of gas we already photographed. A measurement gap closes when we build a better instrument. An understanding gap closes when we think a truer thought, and there is no guarantee about when that arrives. We can even sketch what closing each gap would take, and the 2 look nothing alike. To pin the distance, we would want a ruler that sidesteps the dust and the symmetry problem at once. The light echoes may offer one, since the timing of when each far-off dust sheet lights up encodes the geometry of the whole system directly, without caring how evenly the lobes expanded. We could also, with sharp enough instruments, try to split the single smear of light into its 2 separate stars, or track the 5.5-year clock across many more cycles to watch the orbit slowly change in real time. Those are difficult, but they are the ordinary kind of difficult, the kind that yields to better tools and more patience. Closing the understanding gap, the actual physics of the eruption, may instead take something we cannot put on a schedule, a truly new idea about how giant stars come apart. This is not a fog we are lost in, and it is not a void where knowledge should be. We are not staring at a blank. We are standing at the sharp, well-lit edge of an active investigation, holding a long list of things we have firmly established and a shorter, precise list of things we have not, and knowing exactly which is which. Naming the shape of your own ignorance, Drawing a clean line between what you have measured and what you have only inferred and what remains open is not the same as being ignorant. It is one of the more disciplined things a mind can do. The questions left over are not a mystery hanging over the star. They are the specific, nameable frontier of what we are still working to learn. We know an enormous amount about Eta Carinae, more than we know about almost any other star of its kind, because it is close enough and strange enough to have rewarded 2 centuries of attention. And we still cannot tell you its distance to better than a rough neighborhood, or say with certainty what happened in the 1840s, or count its original stars without an argument. Both of those things are true at once, and neither one cancels the other. That double truth, deep knowledge and stubborn open questions living side by side, is simply what the real study of a hard object looks like. It is not a defeat. It is the view from the frontier. For all the arguing over distance and history and the number of stars, there is a single fact about Eta Carinae that almost no one disputes, and it is the heaviest fact of all. This star is going to die. Not in some vague, unimaginable future, but soon, by the reckoning of the cosmos, in a way that fits everything we understand about stars this massive. So the question that pulls us forward is not whether it ends, but how, and how soon, and what it will look like when a star this size finally loses the long fight against its own gravity. The reason this star's death is close has nothing to do with age in the way we usually mean it. Our sun will live for roughly 10 billion years, burning its fuel slowly and steadily. Eta Carinae will not get anything close to that. A star that massive, that luminous, is spending its fuel at a rate that would drain the sun almost instantly by comparison. Remember how steeply brightness climbs with mass. 100 times the sun's material, but millions of times its light, and every bit of that light has to be paid for by burning fuel in the core. So the most massive stars are not the long-lived ones. They are the ones that burn out fastest, living only a few million years from birth to death, a single brief flash by the clock of the cosmos. Eta Carinae is already deep into that short life. It is not a young star with time to spare. It is an old one, by its own reckoning, running low. To feel the trade it is making, think about a candle. A candle that burns 10 times as bright does not last a tenth as long. It lasts far less than that, because pouring out that much more light demands pouring out fuel at a punishing rate. A star works on the same brutal economy, only steeper. By shining as fiercely as it does, Eta Carinae has committed itself to devouring its own core at a speed no ordinary star ever approaches. The very brilliance that made it visible across 7,600 light-years is the same brilliance that is hurrying it toward its end. It is spending itself to be seen. For most of its life, a star fuses hydrogen into helium in its core, and that stage lasts the longest. When the hydrogen runs low, the core contracts and heats, and the star begins fusing helium into carbon. When the helium is spent, it moves on to burn carbon, then oxygen, then heavier elements still, each stage packed into the center like the rings of an onion, the heaviest at the core. And here is the merciless part. Each new stage releases less energy and burns through far faster than the one before. Hydrogen burning can last millions of years. The later stages, fusing the heavier elements, can last mere centuries, then years, then, in the very last stages, only days. The star is racing through its remaining fuel faster and faster, sprinting toward a wall it cannot see. That wall is iron. Every fusion stage until now has released energy, pushing outward, helping hold the star up against its own gravity. But iron is where that stops. Fusing iron does not release energy, it consumes it. When the core finally builds up a center of iron, the star has reached a fuel it cannot burn for profit. Trying to fuse it takes energy out of the core rather than adding it. So the outward push that has balanced gravity for millions of years suddenly has nothing left to feed it. The furnace, at its very center, goes cold in the only way that matters. It stops pushing back. What follows is the fastest catastrophe in the life of a star. Once the iron core grows past a critical size, a little over 1.5 times the mass of our Sun, it can no longer hold itself up, and it collapses. Not slowly. In less than a second, a core larger than our entire Sun falls inward on itself, crushing down from something the size of a planet to something the size of a city, until the matter at the center is packed as densely as the inside of an atomic nucleus. That infalling matter slams into the suddenly rigid core and rebounds, and a flood of ghostly particles called neutrinos pours out of the collapse, dumping a staggering amount of energy into the star's outer layers. The outer body of the star, no longer held by a core that has vanished into a dense knot, is blasted outward in the explosion we call a supernova. The core that remains becomes either an incredibly dense neutron star, or, if enough matter falls back, a black hole. That flood of neutrinos is not just a line in a model. We have caught it happening. When a massive star died in a small galaxy neighboring our own, back in the 1980s, detectors buried deep underground on Earth registered a brief burst of neutrinos. Only a couple dozen particles, arriving a few hours ahead of the light of the explosion. A couple dozen faint particles, out of the almost unimaginable number the collapse actually released, were enough to confirm the entire picture. The core really does announce its death first in neutrinos, and only afterward in light. So, when we describe the collapse waiting inside Eta Carinae, we are not merely guessing at a mechanism. We have already heard another star go through it. Stars at the extreme upper end of mass do not all die the same tidy way. Eta Carinae might end in a standard core collapse, blasting its outer layers into space and leaving a black hole behind. But it might do something stranger. Some of the most massive stars are thought to collapse so completely that much of the star simply falls straight into a black hole, with little or no explosion at all, a death that is almost quiet. Others, in a particular range of mass, may tear themselves apart so violently that nothing is left behind, no remnant of any kind. The truth is that the exact death of a star this large sits among the things we flagged before as not fully settled. We know it is coming. We do not know, with confidence, which shape it will take. On the scale of the cosmos, this star is in its final chapter, and its death is imminent. But the cosmic sense of imminent is not the human one. Imminent, here, could mean tomorrow night, or it could mean 100,000 years from now, long after everyone alive tonight is gone, and everyone they will ever know. We cannot read the inside of the core directly. We cannot see how close the iron is to gathering, so we cannot circle a year on a calendar the way we can with the 5.5-year clock. All we can say is that it stands near the end of a very short life, and that the end, whenever it comes, will be sudden when it does. Everything we see of Eta Carinae left it 7,600 years ago. The star as it looks to us tonight is the star as it was in the deep past, and whatever it is doing right now, in its own present, will not reach our eyes for another 76 centuries. So when we ask whether it has died, we have to admit that if it collapsed at any point in the last 7,600 years, the light of that death is still on its way to us, and we would have no way of knowing yet. The odds that it happened to die within that one narrow window are not high, and we should not pretend it is likely. But it is possible. In the strictest sense, we do not know tonight whether Eta Carinae still exists. For now, hold the plainer conclusion: this star will die, in a collapse of its own iron heart. In some form we can partly but not fully predict. At some time we cannot pin down, but that is near by cosmic measure. What we have not yet asked is the question that matters most for us. Down here, 7,600 light-years away. When it does die, what will that death actually mean for our sky and for our world? Because whether the end of Eta Carinae is a harmless, beautiful light or something with real weight for us turns entirely on two things: how far away it truly is and exactly what kind of death it chooses. Suppose Eta Carinae dies as a standard supernova, its core collapsing and its outer layers blasted into space. From 7,600 light-years away, what would that actually look like to us? It would look magnificent, and it would be harmless. A new point of light would appear in the southern sky and swell over days into something brilliant, bright enough to see in full daylight, bright enough at night to cast faint shadows on the ground, holding its place for weeks or months before slowly fading. For a season, our sky would have a second small beacon in it, and then, gradually, it would dim and be gone. That is the whole of it, a spectacle and nothing more. We are not guessing about that, because human beings have already lived through it. Roughly 1,000 years ago, stars died within a few thousand light-years of us, and people across the world recorded new lights blazing in the sky, some bright enough to be seen in daytime for weeks. Those were supernovae at distances not so different from Eta Carinae's, and they harmed no one. They frightened people who did not know what they were, and they left behind expanding clouds of debris we can still photograph today. But no crop failed because of them, no life was threatened. They were, for everyone who watched, simply an astonishing thing that appeared in the sky and then went away. The reason such a death stays harmless comes down to how its power thins with distance. A supernova releases a staggering amount of energy, but it pours that energy out in all directions, into a sphere that grows enormous as it travels. By the time that outpouring has spread across thousands of light-years, it has been diluted almost beyond measure. For a supernova to actually endanger life on a planet, to strip away enough of its protective ozone to matter, the dying star would need to be terribly close, within something like a few dozen light-years. Eta Carinae is more than 200 times farther than that. The gap that we spent this whole night struggling to even measure is, for the ordinary kind of death, a moat so wide that the danger never reaches us. A distant dying star does not threaten a planet with heat or a shock wave. Those fade to almost nothing long before they could arrive. The danger, when there is one at all, is chemical. A close enough burst of high-energy radiation striking our atmosphere would break apart the ordinary nitrogen high above us, and the fragments would recombine into compounds that eat away at the ozone layer, the thin shield that blocks the sun's harshest ultraviolet light. Thin that shield, and it is not the dead star's radiation that harms life below. It is our own sun's ultraviolet, suddenly let through a gap in the roof. That slow chemical path is the only way the death of a star reaches down to the surface of a living world, and it only works from close range. But we said the death of a star this massive might not be ordinary, and that is where we have to look harder. When a very massive star collapses to a black hole while spinning rapidly, it can do something a normal supernova does not. Instead of releasing its energy evenly in every direction, it can channel a portion of it into two narrow beams, fired straight out along its axis of spin in a burst of concentrated radiation we call a gamma-ray burst. Think of the difference between a bare bulb lighting a whole room and the same energy squeezed into a tight spotlight. A beam concentrates, and a beam of that kind, unlike the evenly spread blast of an ordinary supernova, could carry real consequence across not dozens but thousands of light years if it happened to be pointed the right way. So for this darker possibility, distance alone stops being the whole answer. The question becomes one of aim. A beam like that fires along the star's spin axis, so everything depends on where that axis points. If it points at us, the beam would find us. If it points elsewhere, the beam misses entirely, and we are simply a bystander watching from the side. And we are not blind to the orientation of this star, because it has drawn its own axis across the sky for us. The two great lobes of the homunculus, the hourglass blown out in the eruption, are stretched along the very axis the star spins around. We can see which way that hourglass is tilted. And it is not aimed at us. The axis of Eta Carinae leans well off to the side of our line of sight, tilted away, so that if it ever did fire a beam along its poles, that beam would be thrown across space in a direction that misses the Earth. First, the most likely death, an ordinary supernova, is harmless at this distance, full stop. Second, even the rarer, beamed kind of death would only threaten us if its aim were nearly perfect, and the star's axis, as far as we can read it, points elsewhere. Third, it is not even certain that Eta Carinae would produce such a beam at all, since these bursts are thought to be uncommon in galaxies like ours to begin with. Stack those together, and the honest bottom line is quiet. When this star dies, the overwhelmingly probable result for us is a brilliant new light in the sky, watched in safety, and remembered as one of the great sky events of whatever age is alive to see it. Not a threat, a gift from a safe distance. Notice what is actually protecting us. It is not that Eta Carinae is a gentle star. It is one of the most violent objects in the galaxy, capable of releasing the energy of a near death and someday a true one. What protects us is not mercy, it is distance and an angle. The same 7,600 light-years we could not pin down cleanly is the exact thing standing between us and any harm, and the tilt of an axis we did not choose is what turns a possible beam away from our world. Move this star a few hundred times closer, or swing its poles around to face us, and the identical death, the same physics, the same collapse, would be catastrophic instead of beautiful. We are safe, not because the universe is kind, but because of where this particular monster happens to sit and which way it happens to lean. Our safety from Eta Carinae is real, but it is bought entirely by geometry. The distance that frustrated every ruler we tried to lay against it is the same distance that keeps its violence far from us. The plain, stubborn number is also the shield. There is a kind of peace in that, once the fear settles. The thing that makes this star hard to measure is the thing that makes it safe to admire. We can look at it precisely because it is far, and we are unharmed by it for the very same reason. Whatever Eta Carinae's death finally proves to be, harmless light or, against the odds, something more, we will not learn of it for 76 centuries after it happens. The verdict on this star is not something we will receive in real time. It is a message that has to cross the same gulf everything else about it has crossed, at the speed of light, taking thousands of years to arrive. And as we noted before, that message may already be on its way. The death may already have happened, its light already traveling toward us through the dark, still years or millennia from reaching our sky. So the final thing to understand about this star is not about the star at all. It is about what it means to be the one waiting at the far end of that light, receiving a universe that is always, by its very nature, already old. There is a top speed to how fast news can travel, the speed of light, and nothing outruns it. Not just light itself, but any signal, any influence, any word that one place in the cosmos could send to another is bound by that same ceiling. So every time we look at anything far away, we are not seeing it as it is. We are seeing the light that left it, carrying a report that is already out of date by the time it reaches our eyes. The universe does not let us see the present of a distant thing. It only ever hands us the past, still in transit, finally arriving. We tend to think this is a strange affliction of deep space, but it is the plainest and most universal thing there is. The sun you feel on your face is about 8 minutes old. If it went out, you would enjoy 8 more minutes of sunlight before the dark caught up. The full moon is a little more than a second in the past. The far wall of the room you are in reaches you a few billionths of a second late. Even a face across the table is not quite the face of now. It is the face of the smallest sliver of a moment ago, the time the light took to cross the space between you. Nothing you have ever seen has been the present. You have spent your entire life looking, very slightly, into the past. Eta Carinae's 76 centuries is not a different rule. It is the same rule everything obeys, only stretched across a much wider gap. Once we see it that way, the delay stops looking like a loss and starts looking like the one thing that makes cosmic history possible at all. Because far away means long ago, the sky is not a snapshot, it is an archive. When we look out to greater and greater distances, we are looking further and further back in time, reading the universe at earlier and earlier stages of its life, all of it laid out at once across the depth of the sky. If light were instant, if we saw everything as it is this very moment, we would lose all of that. The past would be gone the instant it happened, unreachable. The finite speed of light is the reason the history of the cosmos is still visible, still arriving, still there to be studied. The delay we might resent is the only door we have into everything that came before. What the delay does take from us is not knowledge, it is conversation. Recall how, at the very start, a single exchange with this star would outlast every language now spoken, a question taking 76 centuries to arrive and any answer another 76 to return. We cannot talk to Eta Carinae. We cannot poke it and watch it react, cannot run an experiment on it, cannot ask it to hold still. But look at everything we have done tonight without any of that. We measured its distance, read its composition, timed its heartbeat, traced its winds, reconstructed its violent history, and reasoned out how it will die. All of it from light alone, received and studied. The speed of light limits what we can touch and what we can ask. It does not limit what we can come to understand. We keep asking what Eta Carinae is doing right now, tonight, in its own present, whether it still exists, whether it has already died. But the universe is not arranged so that there is a single shared, now we could reach across that distance and check. The idea of what a faraway thing is doing at this exact instant across thousands of light years is not something we can observe, and in the physics of space and time, it is not even a cleanly defined, shared moment the way our everyday intuition assumes. The present of Eta Carinae is not hidden from us like something behind a wall we could walk around. It is simply not available, not to us, not to anyone, not by any means. All that is ever available, anywhere, to anyone, is what has arrived. So bring that back to the death we have been circling. The collapse of this star is one of two things right now. Either it has already happened, and the light of it is somewhere out in the dark between us, crossing the gap, still years or centuries from our sky, or it has not happened yet, and the message has not even begun. And there is nothing we can do to find out which, except wait for the light to arrive. That waiting is not a special torment reserved for this one star. It is the ordinary posture of everything alive in a universe with a speed limit. We receive. We do not get to peek ahead. We will know when the light reaches us, and not one moment sooner, and that is simply how it is arranged. We are not being cheated of the present. There is no vantage point anywhere from which the whole universe is visible as it is this instant, no privileged observer who gets the real-time feed. Every conscious thing that has ever looked up, anywhere, has been a receiver, taking in a world that is always already a little older than it appears. To exist inside space and time is to be perpetually, gently behind, catching light that has been traveling toward you, some of it for moments, some of it for thousands of years. That is not a deprivation to grieve. It is just the texture of being here, of being made of the same stuff as the light and bound by the same rules. We do not have to hold vigil over Eta Carinae, straining for its present, because its present was never ours to have. Whatever it is doing tonight, we are not meant to know tonight. The light will come when it comes. Our part is not to reach across the gap, but to be here at the far end of it, ready to receive whatever it eventually sends, the way we have received everything else it has told us so far. There is a quiet dignity in that role, the role of the one who watches and waits and reads what arrives, without needing to hurry the light along. Still, sit for a moment with how much that patient watching has actually given us. We are only ever receivers of this star. We will never visit it, never stand near it, never sample its gas or measure it up close. Everything we claim to know about 100 solar mass monsters 76 centuries away, we pulled from nothing but the faint light it has been sending across that emptiness. And from that thin, ancient stream alone, we built a distance, a mass, a rhythm, a history, a death. So the question that remains is almost a marvel in itself. How did we ever manage to learn so much, in such detail, about something we can only ever watch from the far side of an ocean of light? The answer is that light is never empty. We tend to think of a star's light as just a glow, a brightness, and a color, and if that were all it carried, we truly could not know much. But light is a far richer message than that. Woven into it is a detailed record of the matter that made it, the temperature of that matter, how it was moving, how dense it was, even the magnetic fields it passed through. A single beam of starlight, properly read, is not a faint smudge from far away. It is a dense, coded report, and most of what we know about Eta Carinae came from learning to decode it. The first key is to stop looking at the light all at once and spread it out. When we pass starlight through an instrument that fans it into its separate colors, the way a prism spreads sunlight into a rainbow, something remarkable appears in the band of color. It is crossed by sharp lines, bright ones and dark ones, at very precise places. Those lines are not random. Each chemical element, when it is hot, emits and absorbs light only at its own exact set of colors, a pattern as specific as a fingerprint. So when we see a particular line fall at a particular place, we are reading the presence of a particular element, directly, from thousands of light years away. This is how we know the gas around Eta Carinae is heavy with nitrogen. We did not sample it. We read its fingerprint in the light. Those same lines carry more than a list of ingredients because they also record motion. When the thing giving off a line is moving toward us, the line shifts slightly toward the blue end of the spectrum. When it moves away, the line slides toward the red. It is the same effect you hear when a siren rises in pitch as it races toward you and drops as it passes, only written in light instead of sound. By measuring exactly how far each line has shifted, we measure how fast the gas is moving and in which direction. This is how we clock the winds streaming off the stars, how we trace the two lobes of the hourglass rushing apart, how we caught that impossibly fast material in the echoes of the eruption. The motion of things we can never touch is written into the color of their light, and we have learned to read it down to a few kilometers a second. The shapes of those lines tell us still more. A line is never infinitely sharp. It is smeared and broadened, and the exact way it is broadened encodes the conditions in the gas. Hot, fast-moving gas smears its lines wide. Dense gas broadens them in its own particular way. Gas caught in a strong wind stretches its lines into telltale shapes. So from the width and the form of a single line, we can read a temperature, a density, the speed of an outflow, without ever leaving the ground. One narrow feature in a spectrum, and folded inside it are numbers we could otherwise never reach. And visible light is only one window of many. Eta Carinae also shines in kinds of light our eyes cannot see, and each kind shows us a different layer of the same object. In infrared light, the long waves that slip through dust, we can peer partway through the shroud that hides the star and see the warm dust glowing. In X-rays, we see the searing collision where the two winds crash. In gamma rays, we see the signature of particles driven near light speed. In radio waves, we see the cooler, ionized gas. No single window shows the whole star. Each one reveals a layer the others miss. What we call our picture of Eta Carinae is really many pictures, taken in many kinds of light, laid carefully over one another until a whole object emerges that no one wavelength could have shown us alone. There is one more instrument in all this, and it is the quietest one: time. A single glance at this star tells us far less than a long, patient watch does. We measured the hourglass expanding by comparing images taken years apart. We nailed down the 5.5-year rhythm by following it through cycle after cycle. We traced the star's history back across centuries by gathering the records of everyone who noted its brightness, from a faint fourth magnitude speck in the 1600s to the blaze of the 1840s and its long fade after. Much of what we know did not come from any one observation. It came from holding a steady gaze on this star across generations and watching what changed. Patience, it turns out, is one of the sharpest tools we have. Now weigh how much of this depends on one piece of luck, the plain fact that this star is close. The most massive, most extreme stars are rare, and almost all of them sit far across the galaxy, or in other galaxies entirely, so distant and so dimmed that they are little more than faint dots we can barely study at all. Eta Carinae is the great exception. It is the nearest of these true monsters, close enough that every technique we have described actually works on it in fine detail. That makes it something precious, a nearby specimen of the most violent kind of star, near enough to dissect with light. What we learn here, from this one accessible giant, we carry outward and apply to all the distant ones we can never study this closely. This single star teaches us how a whole rare class of stars lives and dies. We will never go to Eta Carinae. No human hand will touch it. No craft will ever reach it. No instrument will ever sample its gas up close. By every ordinary meaning of the word, it is utterly beyond us, 76 centuries of light away, hidden behind its own dust. And yet we know what it is made of. We know how fast its winds blow, how heavy it is, how its heart beats every 5.5 years, how it erupted, and how it will die. We reach this star, not with our hands, but with our attention. Generations of people pointed instruments at a faint smudge in the southern sky, spread its light into ribbons, compared its images across years, and patiently pulled an entire life story out of a beam of ancient light. We never crossed the distance. We understood across it instead. Every method we have used, every act of knowing, was the same thing at its core. Something left that star, crossed the enormous gap, and arrived here, and we were waiting to receive it. The ordinary light that let us read its chemistry, the echoed light that let us watch its eruption, the particles it flung into the galaxy, the flash of its death, already traveling or soon to come. Every one of them is the gap being crossed, again and again, in a different form. So before we let this star go, we should look squarely at that pattern, because it says something about what distance really is, something we have been circling from the very first minute. Every single thing we have come to know about this star arrived the same way. It crossed the gap. The ordinary light we read for its chemistry crossed it. The blaze of the 1840s that people watched with their own eyes crossed it. The echoed light, taking the long way around off distant dust, is still crossing it, arriving a century and a half late. The particles flung out of the wind collision are crossing it right now, and the flash of its eventual death is either crossing it already or about to begin. One gap. 7,600 light-years of it, and it is being crossed constantly, in form after form, all the time. The light comes straight, from one point, stamped with a date, so cleanly that we can trace back along it and say the star sits exactly there. The particles come the opposite way, bent and scattered by the galaxy's magnetic fields until they arrive from everywhere at once, stripped of their direction, smeared across millions of years, carrying no return address at all. Same star, same gap, two completely different kinds of arrival. So even the plain question of how far away it is does not have a single answer. By its light, it is a sharp point 76 centuries away. By its particles, it is a presence already mixed into the air of the room around you, with no clean distance at all. We began by treating the distance as a wall, a vast, empty separation, so wide that a question sent across it would outlast our languages, so wide that no craft we could build would ever reach the other side. All of that is true. The wall is real, and it is enormous. But a wall you cannot walk through can still be a wall that things pass through without pause. Light passes through it. Matter passes through it. The star's own past passes through it, arriving late. Its future death will pass through it. The separation is complete in one sense, that we can never go there and never speak to it, and it is barely a separation at all in another, because the star reaches us endlessly, in form after form, every second of every night. This is what the plain word distance has quietly become over the course of the night. We reached for one number, a clean measure of how far, and we could not even get that cleanly, held back by dust and by a shape we can no longer trust. But the deeper trouble was never really the precision. It was that how far is not one thing here at all. There is the distance the light travels, and the distance the particles wander, and the distance in time between the stars present and ours, and none of them agree, because none of them are the same kind of measurement. Distance, which we grabbed for as the simplest fact about this star, proved to be a bundle of different relationships wearing a single word, and prying that word apart is most of what we have actually been doing all night. So when we ask whether the real distance to this star is stranger than we expected, the honest answer is yes, though not for the reason we might first have guessed. It is not strange because it is large. A neighbor in our own galaxy is not a frightening thing, and we settled that in the first few minutes. It is not strange because it hides a threat, since that very distance is what holds the danger away from us. What is strange, if anything is, runs quieter than fear. It is that the tidy idea we began with, that far away means sealed off, cleanly separate, safely out there, simply does not hold up. The most distant thing we have studied tonight is also, in ways we never intended to find, continuously here, far and present at the same time, and both of those completely real. There is more comfort in that than there is dread, once we stop expecting the universe to be a set of sealed rooms. Nothing in the cosmos is truly cut off from the rest of it. The largest gaps we know of are crossed, endlessly, by light on its long straight journeys, by matter on its wandering ones, and by the slow arrival of ancient news. We are not islanded here, staring out at a dark we have no contact with. We are sitting in a steady, gentle rain of signals from the farthest places, most of them too faint or too slow or too quiet to notice, but arriving all the same. The dark between the stars is not empty, and it is not silent. It is thick with things in transit, crossing distances that look impassable, reaching places that look unreachable, including this one, including the ground you are lying on right now. It might even be that total isolation is not a real physical state at all, only an idea we carry over from everyday life. Down here, two things are separate when nothing passes between them, when a wall or a distance holds them fully apart. But at the scale of the cosmos, there is always something passing between. Light reaches across any gap given enough time. Gravity extends without limit. Particles drift for millions of years and still arrive. To be truly cut off, a thing would have to send nothing and receive nothing, ever, and almost nothing in the universe manages that. Eta Carinae certainly does not. It has been in quiet, constant contact with us the entire time, long before we knew its name, sending light and matter across the gap toward a planet it will never know is receiving them. There is real physics under that, not only a comforting thought. The forces that reach across space do not have edges where they simply stop. The gravity of that giant does not extend for a certain distance and then quit. It weakens as it spreads, growing fainter and fainter. But it never actually falls to nothing. Not at 76 centuries of distance, not anywhere. The same holds for the electric and magnetic fields carried by every charged particle. Their reach thins without ever arriving at a clean zero. So, in the strictest accounting, every mass and every particle in the universe is already pulling on and pushing on every other, this star and your own body included, by amounts far too small to ever measure, but never quite equal to nothing. Separate, in the everyday sense, is only a word for interactions that have grown so faint we can safely ignore them. It is an approximation, an enormously useful one, and underneath it the true state of things is that nothing is ever fully disconnected from anything else. So the wall we started with has slowly turned into something more like a membrane. Still vast, still uncrossable by us in person, but porous in every direction to what the star pours out. That is the real distance to Eta Carinae, and it is stranger and softer than the frightening number we expected. Not a barrier that seals it away, but a great width that everything the star emits comes across anyway, on its own schedule, in its own form. The gap is not an illusion, the crossing is constant. Both are true, and living with both at once is closer to how the universe actually is than either one alone. And that leaves exactly one crossing we have not followed all the way to its end. Every messenger we have traced tonight stops somewhere outside us, at a telescope, in the upper air, out in the sky. But one of them does not stop there. One of them reaches past all our instruments and comes to rest on the actual surface of your body, in the dark, tonight, in a form so faint you have never once felt it. The same force that nearly tore this enormous star apart is, at this very moment, resting on your skin. So the last thing left to understand is not out there across the gap at all. It is the smallest and nearest crossing in the whole story, the one that ends right here, where you are, as you begin to let the day go. Think back to the force that nearly destroyed this star, the one we spent so long on. A star so luminous that the pressure of its own light, pushing outward on its own matter, almost tore it apart. The push of light against matter, strong enough to unmake a giant. That same force, the very same physics, is resting on your skin right now, in this room, in the dark. Not something like it, not a distant cousin of it. The identical force, light leaning on matter, is touching you tonight, at a scale so small you have never once noticed it. Here is how that can be true. Light carries momentum, a capacity to push, and whenever it lands on something and is absorbed, it delivers a tiny shove in the direction it was traveling. The glow from your lamp, the last light of your screen, the faint starlight slipping through the window, all of it is striking your skin and giving you a small push as it arrives. It is the same push that streams a comet's tail away from the sun, and the same push that, multiplied across the unimaginable output of a giant star, can drive that star to the edge of coming apart. One phenomenon, light pressing on matter, playing out on a comet, on a monster 7,600 light-years away, and on the back of your hand, all by the same rule. The only difference is the amount. On Eta Carinae, the light is so overwhelming that its push rivals the gravity of 100 suns. On you, tonight, the push of all the light in the room is so faint that no instrument you own could register it against your body. It is far too small to feel, smaller than almost any force you could name. But it is not zero. As we found a little while ago, these things thin toward nothing without ever quite reaching it. The light in your room really is pressing on you, gently, continuously, by an amount too small to matter and too real to be nothing at all. Let that close the distance we have been measuring all night. The equation that decides whether a star holds together or tears itself to pieces is the same equation describing the touch of your reading light on your eyelids. Not a comparison, not a poetic echo. The same law, written once, governing both the largest and the smallest version of the same thing. The monster at the far end of that gap and the lamp an arm's length away are doing the identical physics to the matter in front of them. The scale is almost incomprehensibly different. The rule is exactly the same. The light that told us what this star is made of, the echoes that let us watch its eruption, the particles drifting through the galaxy, the flash of its death, already crossing the dark toward us. And now this, the faintest crossing of them all, the push of light coming to rest on your own skin, obeying the same rule as the star that made it. The distance we chased and could never quite pin down does not end out there in the cold. It ends here, on you, in the quiet, tonight. There is nothing left to reach for now. We have followed this star as far as it can be followed, from a faint smudge in the southern sky all the way down to a whisper of pressure on your resting body, and the whole of that journey was the same physics, unbroken, from the giant to the lamp to you. You do not have to hold any of it. You do not have to solve the distance, or settle the merger, or wait for the death that may already be on its way. All of that will keep out there, crossing the gap at its own slow pace, whether or not anyone is awake to receive it. For now, let the light in the room grow soft. Feel the weight of your own body settling into the bed beneath you, held down by the same gravity that holds a star together, the plainest force there is, asking nothing of you but to let go. Let your breathing slow. The day, with all its questions, can be set down now, the way you would set down something you have carried a long way and no longer need to hold. The universe reaches you gently. It always has. Light that traveled 76 centuries, and light that crossed the room, arriving at the same skin, pressing with the same faint touch, asking for nothing in return. You were here for all of it tonight, awake at the far end of that long, quiet arrival, and that was enough. Thank you for spending this stretch of the night with me. Rest well and sleep deeply.